Good morning to everybody. We are waiting for the last connection, so it's a pleasure to welcome all of you in the remote section of the conference, and we will have an intense program. Okay, Franco, great. We're waiting. You.
Mi sentite? Mi sentite adesso?
Yes, we can hear you. Wonderful.
Okay, good. Okay.
Good. Okay, so it's a pleasure to welcome all of you here this morning. We had 3 beautiful days in presence, and now we are getting a very exciting section in remote, hoping that one day we can do this all together here. And it's a real pleasure to introduce Franco Nori. It's a well-known scientist. He's one of our 4 keynotes. Franco, thanks for being us with here. I would like to, Franco is in Japan now, and to be safe, it's already recorded, the one. So we'll make it run from here from Napoli. Franco will be here. We'll respond to the questions at the end. Is it correct?
Yeah. But my talk is recorded, so there is no need to record it again.
No, absolutely. It's recorded in the sense that we'll, just to explain to everybody. There is here Franco Porzo will co-chair with me this session, and we are here at University of Napoli in one of our rooms. And okay, so we make it run. 1 second. Okay. Obviously, needless to say that we have our young collaborators.
Ciao.
Obviously, needless to say that we have
I'll be talking today about virtual photons in ultra-strongly coupled systems, and also about quantum nonlinear without photons. I'm in Riken, Saitama, and also the University of Michigan, Ann Arbor. Let me start with a brief haiku. It's a short Japanese poem of 3 lines. I would like to thank the organizers for their kind invitation. I will start with a brief introduction to light-matter interaction. Other interactions or photons inside cavities, so this will be standard material, so please fasten your seatbelts. Let us consider an atom inside a cavity. In the cavity, the photon is bouncing back and forth many times and is interacting with this atom inside via the dipole moment. And this which are roughly 1,000 times larger than typical atoms. This is like considered the hydrogen atom for large N values, let's say 60, 80, 100 or so. The atoms are roughly 1,000 times larger than typical atoms. They are sent to the cavity one by one, and at the exit, the atoms are being measured, and they can reveal the presence or absence of a photon inside the cavity. The cavity is made of a superconducting niobium, their mirrors, and inside the small cavity, it's about 2.7 centimeters, about an inch, for more than a tenth of a second. Before it disappears, the photon will have traveled a distance of one trip around the Earth. So this is done to maximize the light-matter coupling, which is very weak. And this was done by them in the 70s and 80s and later on in the 90s and so on. So there's been work for a long time in coupling natural atoms, typically Rydberg atoms, with a cavity. And here the physics is you excite the atom, you move into the cavity, and then interacts with the cavity. So you're exchanging photons back and forth between the atom and the cavity. So the atom absorbs a photon, then emits it, and so on. Now, in this century, this natural atom has been replaced in many experiments by superconducting qubits. Could be either charge qubits, flux qubits, and phase qubits, and a variety of different versions of them. The flux qubit is an early version where there is a superconducting loop with three barriers. These are three Josephson junctions indicated here by these X's, and they're coupled. This artificial atom is coupled to an LC resonator via mutual inductance. So this artificial atom is interacting with this cavity, and this replaces what was done last century and also this century with this configuration. You're exciting the artificial atom or two-level system or qubit and bring it to resonate with the resonator. And then the system is the ground state, absorbs a photon, is excited, emits a photon, it decays and goes back and forth and eventually decays. The advantage of this artificial atom superconducting system is that there is a much stronger coupling strength. Much stronger means about 5 orders of magnitude stronger. So this is a huge difference that it is not possible to obtain with natural atoms. Their locations are fixed. You can have arbitrary interaction times and there is scalability. You can put several of these atoms in any place you want inside the cavity. So therefore, that's why there are many people in this century using these artificial atoms to study light-matter coupling because of these many advantages summarized here. If you wish to read more about atomic physics and quantum optics using superconducting circuits, there is here an 11-page pedagogical review. There are almost no equations there, and it's available free PDF on our website, and it's fairly easy to read. It's non-technical. If 11 pages is too long, there is a version which is half, is in Physics Today, and the 3-line summary is the following. Superconducting circuits can behave like atoms, make a transition between 2, 3, or 4 different levels, could be more. These circuits can test quantum mechanics at macroscopic scales and can be used to conduct experiments in quantum optics and atomic physics on a silicon chip. So, and this PDF is available on our website. A more recent review, 2019, is this one here. Is a very recent introduction. It's a bit longer, but it's fairly pedagogical. The website is freely available on our website. This is open access, also from the publisher. And if you wish to read more, we have a longer overview with almost 1,400 references on how to do microwave photonics with the superconducting quantum circuits, which are artificial atoms, which have become very trendy in the past 20 or so years in many different labs around the world. It's a different way to do quantum optics. The way to model this system is via Hamiltonian called the Rabi model, where there is here the term describing the resonator. The two-level system is a diagonal sigma z, spin down, spin up, ground state, excited state. And this is the coupling, interaction energy, also known as dipole interaction energy or Rabi frequency. And of course, there are energy losses because eventually the photons escape. The energy of the resonator is in general different from the qubit, but in this case, they're taking the same to simplify the notation. So the energy scales are this bare energy, and then the dipole interaction energy and the energy losses. When you increase the dipole interaction energy or Rabi frequency, you increase it beyond the losses, beyond 10% or so of the cavity frequency or even larger, and then you get the system from a weak coupling, strong coupling, ultra strong, deep strong coupling. So here you can set the Purcell effect, Rabi oscillations, virtual photons dress in the ground state, they renormalize the ground state, and this can be seen in superconducting circuits, also in quantum wells, in terahertz waveguides of aluminum arsenide, aluminum gallium arsenide, and also there are more and more groups moving from the strong to ultra strong, and some of them even reach the deep strong coupling regime, where instead of having a renormalized ground state, you have an entangled ground state. The atom and the cavity are essentially completely intertwined and inseparable. And so there have been a significant progress over the years to increase this coupling. This is mostly last century, this is mostly this century, and in the past few years. I'll be focusing mostly on strong, ultra-strong coupling. There are different strategies to reach this regime. Serge Haroche and Jean-Michel Raymond, in this beautiful book and many other reviews they had, they explain that they use Rydberg atoms, which provide high dipole moments. You need this to couple light and matter, and also very good mirrors to minimize the decay rate. Several groups in the past few years are considering other systems, let's say electron gas in a quantum well, where there is a collective enhancement of these main electrons, and also these superconducting circuits where you can create one-dimensional resonators in a small volume, and they can achieve a very large effective dipole, the capacitive coupling or inductive coupling. A pedagogical review on the ultra-strong coupling regime between light and matter was published very recently here. Is the first review of this journal here, and so far is the most cited one. It's available also on our website, so all these reviews are available for free on our website. We have publications and also presentation, both PDF and PPT are available free of charge in our website. Just Google publications and my last name and you can find it very quickly. So let's look at the Hamiltonian here. So we have oscillator, two-level system, and the light matter coupling. Let us turn this to 0. And let's look at the first term here. So in this case, the field inside the cavity can have n photons, could be 0, 1, 2, 3, 4. So that's very simple. You can, and the atom can be either in the ground state or excited state. It's a sigma Z matrix. Essentially, it's either spin down, spin up. So therefore, to describe the system, you need to have an integer here and ground state and excited state. That's very simple. Now let's turn on this term. What happens when you increase the light matter coupling? So let's do it slowly, one term at a time. So we turn this term, and then when the interaction is weak enough compared to the other energy scales, it is possible to neglect the so-called counter-rotating terms, which are here, obtaining the so-called James-Cummins Hamiltonian, which is this one here. So this is the James-Cummins Hamiltonian, also known as JC abbreviated. And as you can see, the excited states now hybridize. Instead of having 0, 1, 2 photons in the cavity and ground state, you can get these superposition states. The ground state doesn't change. The ground state means there are 0 photons in the cavity and the atom is in the ground state. So you can increase the coupling and nothing happens to the ground state. Now, what happens if you keep ramping up this more and more? Then you need to take into account these terms. You need to go beyond the rotating wave approximation. And then in this regime, the ground state is in a coherent superposition of state that have different number of bare excitations. So it can be either 0 photons, ground state, 1 photon, excited state, 2 photons, ground state, etc. So therefore, in this case, the ground state is actually shifted. All the energies are shifted, and this is the two-level system analog of the Lamb shift. What Lamb did when to obtain the Nobel Prize was to notice the energy levels of the hydrogen atom were shifting in the regime where they can actually interact with the vacuum. That was the origin of quantum electrodynamics in the 1940s when Lamb was doing these experiments there. Actually, in the 1930s, actually. So therefore, we have here light matter at rest states. In the ultra-strong coupling regime, the expected number of photons in the ground state is non-zero. These are called virtual photons, since they cannot be spontaneously emitted, because the ground state has the lowest energy. They actually cannot decay. So therefore, there are photons in the ground state, but these cannot be emitted because this is the lowest energy available to the system. In classical physics, the vacuum is empty. In quantum mechanics, the ground state has 0 point energy. So therefore, there are fluctuations even in the vacuum state. So the vacuum has fluctuations. It's empty on average, but these fluctuations can be described as virtual particles that can spontaneously appear and disappear in pairs. And so these vacuum fluctuations are often represented as these virtual particle bubbles where they appear and disappear in pairs. And then what Moore in 1970 proposed, and it's called the dynamic Casimir effect, but it's not due to Casimir, it's due to Moore in 1970, is to break these virtual photon bubbles by putting a mirror oscillating very fast. If the mirror oscillates very fast, then it will break these bubbles over and over, and then creating correlated photon pairs, because this particle had this origin, the same origin. So this is the simple explanation of the dynamic Casimir effect or the Moore effect. The event horizon in a black hole acts like a very fast moving mirror breaking virtual pairs. So therefore, what Hawking realized a long time ago is that the event horizon is also breaking these virtual pairs. When the virtual pairs occur away from the event horizon, they're not broken, but here they're broken. So, but then in this case, 1 photon is emitted as opposed to 2 photons. So at this event horizon, the pairs of virtual particles are broken up, with one being trapped and the other one escaping. It was done in the 1970s. There are several physical phenomena which are due to quantum fluctuations with no classical counterparts. And then we have, actually, sorry, Lamb was 1947. There was some other papers in the 30s. So in the 1940s, experiments of Lamb gave rise to this impetus on work in quantum electrodynamics. Around that time, Casimir proposed the Casimir force, but this is the force among 2 plates, static plates. And then dynamic Casimir corresponds to this oscillating mirror, creating correlated photon pairs out of these vacuum fluctuations. In the 1970s, 74, 75, Hawking did his prediction of a similar effect, 1970, 1974, and so on, 75. And then Unruh predicted the Unruh effect, which is somewhat related to this. All of these effects on quantum vacuum effects are pedagogically described in this review of ours, which is available on our website, in case you're interested on the relationship between these effects. I will not describe them now. I'll be talking about this briefly in my next talk. To observe virtual photons, you can do a non-adiabatic modulation of the coupling. So it's how to force virtual photons to be emitted. We propose to do a non-adiabatic modulation, namely the mirror is replaced by an electromagnetic mirror, which oscillates very fast. I'll describe afterwards in a separate talk. And this is driven by a magnetic flux oscillating very fast inside this squid. These are two Josephson junctions in parallel. And the theory and the experiment were done in collaboration with Chalmers. Here, the experiment was done there. We only were working on the theory. And then the idea is to replace the mechanical mirror that oscillates very fast by an electromagnetic one in a superconducting circuit. Now let's go back to these virtual photons in ultra-strongly coupled systems. This work done in collaboration with Kokum, Savasta, Di Stefano, Macri, Stasi, Garciano, and Miranovic, located in Sweden, Italy, Poland, and we often meet in Japan. And this is a brief history of time, a brief history of the time of optics. So a long time ago, people were studying probably very many photons, classical optics. Over time, few photons, quantum optics. Then one photon, quantum optics. And if you see the historical trend from very many photons, few photons, one photon, the next step is to consider quantum optics with no photons, could be called Zen quantum optics, or vacuum quantum optics, where we are taking into account these vacuum fluctuations. One way to take this into account is to consider two atoms in one photon simultaneously exciting both of these atoms, which cannot be done directly, but can be done indirectly via briefly borrowing a second photon from chance fluctuations in the vacuum within the cavity. And this allows the transition from here to there. This can be computed analytically and numerically. And so therefore, the last end of our preparing was we hope that this work on one photon simultaneously exciting two or more atoms could simultaneously excite two or more referees. Indeed, it simultaneously excited three referees and also the editor, chosen as editor's choice. Hamiltonian has this resonator mode, intracavity field operator, the qubit Hamiltonian, there are two in this case. And the coupling has in general this sigma z and in general sigma x. This one is parity breaking and the one not. The coupling strength can be increased. When you plot the energy of the system as a function of the cavity or the frequency of the cavity, divided in units of the frequency of the qubit, you can see there are several level crossings, but when you magnify them, these are not level crossings. These are avoided level crossings where the two atoms in the ground state are simultaneously excited by a single photon, bringing them excited and then back to the ground state and excited back to the ground state. And this corresponds to maximally entangled three-particle states. And this can be proven in many different cases. If you start with the system we described, you have a coherent input pulse driving the cavity. So at a certain time here, you drive the system right there at this avoided level crossing. Then what happens? Then this is the pulse. And then you're pumping one photon in the cavity. But the photon is absorbed by the two atoms. These two qubits are excited. Then the qubits emit the photon. So the photon is in the cavity. And they're going back and forth, exchanging photons between the cavity and the qubit. This when there is no damping. When there is damping, eventually the photon decays out and it goes out. So this can be quantified by looking at the cavity mean photon number, atom mean excitation number, zero delay to atom correlation function. But the idea is that the photon is exciting the two atoms back and forth. So they are exchanging this energy. We also propose physical processes analogous to spontaneous parametric dark conversion, where one excited atom can directly transfer the excitation to two spatially separated atoms with probability approaching one. So this is similar to down conversion. The interaction is mediated by the exchange of virtual rather than real photons. So in reality, there are photons, but instead of being real, they're virtual. But typically, you cannot access them, but there are some tricks people are beginning to play to be able to probe them. And this is going to be a growing field in the future, how to probe, how to use these not only real photons, but also the virtual ones. These nonlinear processes are coherent and reversible. So the pair of excited atoms can transfer the excitation back to the first one. This is the atomic analog of some frequency generation of light. And this can be generalized, as you will say, three-way mixing, four-way mixing, Kerr effect, Pockels effect. So here we have the qubits, the cavity, and the coupling here, interaction Hamiltonian. So there are n two-level atoms, and then you can have, in this case, consider the cavity, 3 atoms, and in this case, consider the frequency of 1 and 2 match the one of 3. And there's these crossings that when you look at them very carefully, they're not really crossing. It means that they're avoid the level crossing. So the ground states of the first 2 atoms are excited and then decay to the ground state. So they're passing the photon energy between 2 atoms back and forth. So these are 3 qubits splitting, can be described by this effective Hamiltonian. Essentially, atom 1 and 2 are excited simultaneously, and 3 decays, and so on. This can be sudden perturbation theory, where you can have, for instance, in this case, the excited atom, number 1, decays and provides a photon in the cavity, which is this one here. So it's a real transition here. And then this photon in the cavity can be used to excite the second atom or the third atom. So these blue lines corresponds to transitions involving real standard photons. The dashed lines corresponds to photons where the system is borrowing virtual photons from the vacuum. So in this case, you're grabbing another photon from the vacuum, and then you get these processes. Some of them involve real photons, other ones virtual ones, and then you get this process here. This is possible to add all of these terms, but there are many, many different possibilities in general how to go from one state to the other one. When the couplings are the same and the frequencies satisfy some simple conditions, it's possible to obtain analytical results. Otherwise, in general, it's numerical. But the main idea is the following: you're having a photon that excites atom number 3, but then atom number 3 decays, and it passes the energy to atom number 1 or 2. So these qubits eventually decay and provide the photon to qubit number 3, and so on. So therefore, this photon is being exchanged between 1 qubit number 3 and qubit number 1 and 2, back and forth. It's a 3 qubit mixing. It's like something like 3-way mixing. Or you could have the following, like in this case, the first atom is excited, decays, and excites the second atom. Or the second atom decays and excites the third atom, or the third decays and excites the fourth atom. So this involves essentially passing the photon between the first and the second, or the second and the third. 1 atom excites the next one, or 2 atoms, or 3 atoms, or 4. This is the analog of 3-way mixing, 4-way mixing in nonlinear optics. In this case, you can get 2 atoms excite number 1 and 4, decay and excite number 2 and 3, and the energy is being exchanged back and forth. This square corresponds to this transition here. So they look like they're crossing, but they're really avoidable of a crossing. So they're actually interacting, and the energy is being exchanged between them. In this case, for instance, atom 1 and 4 are excited, and then they decay and pass the energy to atom 2 and 3. And 2 and 3 decay and pass the energy to qubit 1 and 4. And at this moment, there are these 4 particle GSE states, which are very important for quantum information. It's Greenberg-Horn Zallinger states, and this can be generated in this way. So there are a few examples of quantum linear processes that have been presented. Now let's consider a more general theory of this quantum linear optics in the ultra-strong coupling regime. So therefore, this is a different kind of quantum nonlinear optics, which are single atoms and virtual photons. There are more details, explanations, and presentations on the website, but this will be a quick tour. So let's start first with 3-way mixing analogs, and then 4-way mixing analogs, and other nonlinear processes like Kerr effect, Pockels effects, etc. So the simplest system is one cavity with one atom, and they're interacting. So there's resonator, two-level system, frequency of the resonator, A, and the frequency of qubit, omega q. The coupling can be either quantum rapid coupling of this form, which is the dipole coupling between them. And you can have strong coupling, ultra strong coupling, and we want to have at least strong, either strong and ideally even ultra strong. But there are different ways to couple the system. So one of them is the James-Cummings Hamiltonian that conserves the excitation number. So therefore, when the system is excited, the atom is excited, you provide a photon to the cavity, and the photon is absorbed by the atom and going back and forth. In general, when you interact with the quantum vacuum, this is not the case. Essentially, in the general case, there is no restriction on the excitation number because you can actually grab photons from the fluctuations on the vacuum and back and forth. The quantum rapid Hamiltonian is a step in between that conserves parity, which is this operator here, where n is the number of excitations, is the number of photons in the cavity plus the excitations in the atoms. All of these models can be experimentally realized using superconducting circuits, and also they're being studied using collective excitation with atoms in quantum wells, electrons in quantum wells, and other systems. In linear optics, you look at the system, the polarization high intensity. Well, in this case, there is no need to look at high intensity. The effective coupling is mediated by this higher order process with virtual photons. So it's a very different kind of linear optics. Second harmonic generation is typically explained in the textbook like this. You input omega, you get twice omega out in a nonlinear crystal. In this case, you need to have this kind of couplings here between the atoms and the resonator. So you have the excited atom, it decays and provides two photons to the cavity. And this can be done either the excited atom decays to the ground state and then provides a photon to the cavity, and then you borrow a photon from the vacuum fluctuation to come here. So therefore, red are the transitions mediated by sigma z, blue by sigma x. Dash means n is not conserved. In this case, you're actually borrowing or taking photons from the vacuum fluctuation. Solid ones conserve the number of excitations. And here you get from the excited atom decays to the ground state, providing two photons to the cavity. In linear optics, you have single photons. Sorry, in the typical one, you have strong pumping in linear optics. In this case, we don't need strong pumping. Single photons works, no external drive. In standard linear optics, it's often poor efficiency. In this case, deterministic process. So it's very, very different. There are often multi-level atoms in linear optics. In this case, 2 levels is enough. You can do with 3 or 4, but 2 levels is enough. Typically, there are no propagating waves. There are propagating waves. In this case, there are photons are localized in resonators. So it's very different. So let's look at three-way mixing. Could be general way three-way mixing. You have these two lights, two lasers, omega 1, omega 2. You get the sum, or you can get the degenerate, or you can get spontaneous Raman, stimulated Raman scattering. And this corresponds to some frequency generation, different frequency generation. Second harmonic generation, also known as up conversion. Second subharmonic generation, also known as down conversion. And different kind of process, Stokes, anti-Stokes, stimulated Raman scatter. So there are very, very many processes here. Let's look at the summary of three-way mixing in linear optics under deterministic analog with single atoms and virtual photons. So here we have the process could be degenerate two-way mixing, non-degenerate. Because degenerate could be either up conversion, second harmonic generation, or down conversion. If it is non-degenerate two-way mixing, it could be Raman, spontaneous stimulated, some frequency generation, different frequency generation. But in each case, you can have one atom, one resonator, one cavity, one qubit, two resonators, or there are different possibilities. These are the simplest ones. And there are some standard kind of relations to be able to get the excited state to the ground state and provide two photons to the resonators. You need to satisfy this condition here. So there are all these different possibilities. All of these processes change the number of excitations by 1. So they require the generalized quantum rapid interaction. These are described in great detail in a very, very long paper on our website. So let's focus on the processes inside the red box. So this is the red box here, and the red box is down conversion. If we understand this, it's very simple to understand a conversion. It's exactly the same. All arrows are flipped. And these ones here are more complicated version, but the main idea can be understood by these three examples here. Actually, we already saw one of them already. In this case, the excited atom decays to the ground state, provides 2 photons to the cavity. This photon in cavity number 1 produces. So one case, the left panel shows all virtual transitions that contribute to the down conversion process. So we go from, in this case, the one cavity has a photon and decays and provides 2 photons in the next cavity, and the atom is asleep at the beginning and is asleep at the end, doesn't do anything. But there are some intermediate steps. But red means sigma Z, blue sigma X, dash do not conserve, and then the blue solid arrows mark transitions that do not change the number of excitations. These are transitions that are mediated by the terms in the James-Cummings model. The blue dashed correspond to transitions that change the number of excitations by 2, and these can be described in the right model. And the red dashed arrows change the number of excitations by 1. This is the generalized Rabi model. So in this case, you have here 2 resonators, A and B, and 1 atom. They're interacting. And then in this case, the resonator first one decays and provides 2 photons to the second one because it satisfies this relationship here. And then there are different ways to get from A to B. There's no need to go into these details, but there are these virtual levels in between to get from the initial state to the final state. Another example here on this box here is the one shown right here, where you have 1 resonator and 1 atom. So in this case, the atom is in the excited state, decays to the ground state, provides 2 photons, this down conversion. Second regeneration, down conversion to the cavity. And then, and the last one is the one we have seen before, is 1 resonator interacting with 2 atoms, and this photon can simultaneously excite the first atom and the second one, can excite both of them. And these were the discussing before. There are all these processes can be described in detail, but this is so they can be derived. These are all down conversion. If the arrows in the figure are reversed, you get up conversion. So it's so we can get conversion 1, and you can again remember there is here James-Cummings Hamiltonian. The number of excitations is conserved. Quantum Rabi, the parity is conserved. Generalized Rabi Hamiltonian, there is no restriction on the excitation number. All of these models can be experimentally, and there are different groups working on this right now. When n changes by 0 or 2, you can use either the James-Cummings model for 0 or 2 for the quantum Rabi. So depending on the transition, this can be described. This is for 4-way mixing, where there is degenerate, non-degenerate, up conversion, down conversion, hyper-Raman. There are all kinds of possibilities here. And you can also do the following. You can look at multiphoton absorption, higher harmonic, higher subharmonic. You can look at parametric processes. You can look at the Kerr effect, which is one here, A dagger A square, cross Kerr, A dagger A, B dagger B, and the Pockels effect. These are all nonlinear processes. So in summary, we have studied a system with single qubits and resonators in or close to the ultrasound coupling regime, and they can realize analogs of very many nonlinear optical phenomena, including 3-way mixing, 4-way mixing, higher harmonic, subharmonic generation, up and down conversion, multiphoton absorption, parametric magnification, Raman, hyper-Raman, Kerr, cross-Kerr. These analogs rely on effective couplings, which are mediated by higher order processes involving virtual photons between system states. The effective coupling becomes weaker the more intermediate steps you have, and the ultrasound coupling regime is strong enough. This involves single photons, not too many, no external drive, deterministic process, only 2-level atoms, although it can be generalized to 3 or 4. These are new ways to create useful entangled states, a new way to do quantum linear optics, and experiments on CQPD right now are exploring this regime. Some of them have been seen, some other ones are in progress. Thank you very much for your attention.
Franco, thanks so much for your presentation. And I really would like to thank you once again, because you have done exactly what some kind of overview and putting together. I hope that you can hear me. And because at the conference we have different communities, and you have given a wonderful overview and connecting pieces. Franco, can you hear me? Yes.
Okay. Yes, I can hear you. Can you hear me now?
Yes. So I also would like to say that this for everybody, that we have some kind of delays between YouTube and Teams of a minute. So we'll take a bit of time waiting also for
can you hear me now?
Yes, we can hear you.
Hello.
Yes.
Hello. Can you hear me?
Yes.
Hello.
Yes, we can hear you.
Can you hear me?
Yes. Yes. Can you? We can hear you. Sì, il microfono. So Franco, can you hear me?
Yes. There seems to be a delay, like an echo. I see a question by Luigi Palma.
Yes, exactly. Right. Exactly. I want to. Yes, Luigi is asking you: could the regime behind the JC model improve the performance of superconducting quantum circuits?
Yeah. The answer is the following: yes, and we have one paper on how to do long-range connections between qubits. So therefore,
go on, Franco, go on. Franco, keep going. Don't worry. I mean,
okay, the other paper we have is how to improve the memory. So therefore, can you hear now?
Yes, we can hear.
So therefore, there are 3 papers on the quantum computing aspect. One on the extended memories, another one about gates, another one about connectivity. So there are 3 works involving this. So
Franco, don't worry, keep talking. Don't listen to YouTube because they will hear us in 30 seconds. So don't worry, keep going.
Because the YouTube sound is delayed. I see.
Delayed by half a minute or 40 seconds. So it's quite
exactly. So that's why I was confused. I heard my voice like 30-second delay. So the answer is yes. If you look at the following, if you want to learn more about this, we have in our website one page titled ultrastrong coupling. There is a review published in Nature Review Physics, which is the most cited review in this new journal. The journal has been around for 3 years. It's very popular. It's very pedagogical. So therefore it gives a broad overview of this entire field. And that's available for free on our website. If you go to the journal, there is a paywall. If you go to our website, all our papers are for free. And also regarding quantum computing, there is one about how to extend the memory. One of them, how to do connectivity between faraway qubits. Both of them done with Roberto Stassi. He's in Messina. He was a postdoc in our group for 3 or 4 years, and then he joined Messina about a year or 2 years ago. So therefore, we're still working together. And then another one with Vincenzo Macri, who's a postdoc in our group, originally from Messina, also on the gates. So there are applications on the quantum computing side of it, which I didn't mention before. Now, there is another question here about Martina Esposito. Oh, thank you for the comment. Right. Virtual photons. Okay, I see. Okay, can be extended to propagate in waves. Okay, typically here, it's
Franco,
done.
Sorry, let's repeat for everybody. Is there a way to extend this nonlinear quantum optics framework with virtual photons and artificial atoms to propagating waves instead of photons localized in cavities? That's a question so that everybody.
Yeah, we did it in a different context called the dynamic Casimir effect, which should be called the Moore effect, where you have is an open resonator. The open resonator is like a trombone. In a trombone, you change the length of the resonator. When you change the length, the frequency changes. And if you change the frequency very fast, very quickly, then you generate a traveling photons, but these are correlated photon pairs that can be detected. And this was published in Nature some years ago. It became like very highly cited paper, over 1,000 citations. So therefore, there are ways to convert virtual photons into traveling photons, but in different contexts. And this is described in a different web page on our webpage. Is called dynamic Casimir effect, where there are these conversion of a virtual to real photons in using these oscillating mirrors. Also, we have a talk on how to relate this effect on a cavity with, for instance, the Hawking radiation. In Hawking radiation, you're breaking pairs. So one photon is inside the black hole, one photon goes out. In the case of dynamic Casimir effect, which you can do in the lab, both photons are moving the same direction, are correlated. And but actually, there is even a talk. I have a talk online about how to do this. If you look at our website, there are several presentations on this and reviews.
Okay, wonderful. Last question, then we have to go on. And obviously, you can contact Franco Bainer. There is a question from Alima Ahmad. In the strong coupling regime with cavities resonators, two or more qubits may exchange energy by means of photons, real or virtual. Is this energy exchange like a swap mediated by the resonator?
Yes, indeed. We have a paper which is also, well, very popular. It's a theory paper published a few years ago, and the title is "One Photon Can Simultaneously Excite Two or More Atoms at the Same Time." This is counterintuitive. And then, so therefore, and what you do is the following: the photon cannot do it unless you borrow additional photons from the vacuum. And this the same happens with the Lamb effect. In the Lamb effect, the Lamb shift, the energies are renormalized, are shifted. Why? Because in the Lamb shift, or in this regime, the number of excitations is not conserved. You can actually grab photons from the vacuum, and you can put photons into the vacuum. And that's the commonality between the Lamb shift, the dynamic Casimir effect, the standard Casimir effect, the Unruh effect, Hawking radiation, and others, is this ability to be able to access photons from the vacuum. They made them real, and real back to the vacuum. And we just put a preprint in the archive on how to do this in a cavity by sensing the pressure, the radiation pressure at the edges, because it's a. But all of this is explained. We have several pedagogical papers on this online in our web page, and we also have several talks online, including this talk is available online. I see some people arriving late. You can actually see the talk, if you wish, on our website.
Franco, thanks so much. We have to move on. Really, thanks so much. And obviously, for everybody, you can contact Professor Nori Bemi. Thanks so much.
Okay. Yeah.
And,
thank you for the invitation. Thank you.
Now it's a pleasure.
Okay.
Thanks, Franco. Bye.
Okay. Bye-bye.
Bye-bye. Francesco Vedovato give a talk about from University of Padua, advancements on QKD networking space on the ground. And also Alberto is here for co-chair the next section. Okay, Francesco.
Okay, good morning to all. Can you hear me?
Yes, sure.
So, okay.
Let's try to
So, condividi.
share your
Yes. Okay, you should be able to see something now. Can you hear me?
Yes, we can hear it.
Can you also see the...
Yes, but we don't see the full screen version of the transparency. We just see all the transparencies together.
Okay, because if I do riproduce dall'inizio, it doesn't work, so...
Try to visualizzazione relatore, maybe it's right.
Let's try this way.
No?
No. Ok.
Try riproduci dalla diapositiva corrente. Just on the left.
Ok, sorry.
Oh, we lost the sharing.
Yeah. Now you should see. Let's try it this way. No. I think you don't see now the... You don't see all the stuff. Huh? We can do something. So this can be good enough, or do you prefer that I pass in PDF?
It's a little bit small, but we can try. Otherwise, try to go back and share the full screen, the screen and not the window.
Okay.
Just try it, and otherwise we go on this way.
So
Okay, go this way, no problem.
Okay, I restart the sharing. Okay. Can you see something?
Yes.
Okay. So thank you and sorry for this problem, but I am Francesco Vedovato, and I want to give you a brief overview about the activities that we perform at the Quantum Future Group in Padua about the development of QKD systems, in particular with the scope of implementing them in a network in our university and over our city. And the context for this is given by a big project in which we are involved, that is OpenQKD, that is a big European project that has 38 members all around 13, 14 countries in Europe. And the focus of OpenQKD is to bring QKD out of the research laboratories toward the actual and real implementation in the field. So there are a whole consortium that ranges, that span from the builder of the systems, okay, at the physical layer, like university and also some industries, and also the integrators and telecommunication operators. Okay, so it is really a big project that started 2 years ago. And in this project, our role is to study and develop the interplay between satellite and fiber-based quantum key distribution system. In particular, since up to now there are really few satellites, let's say, dedicated to satellite quantum communication and QKD, in particular, there are only this Michus, the Chinese Michus satellite, okay? The idea is to emulate the satellites by using horizontal links with the dedicated transmitter and receiver, okay? And so to study the interplay between the free space segment of the nectar and the fiber-based one. In particular, we, due to the fact that we have to study the free space part, we already made some design choice for our QKD prototypes that are, for example, the use of polarization encoding, okay, to encode the quantum information into the photon, the use of the three-state 1-decoy BB84 protocol, and that is the simplest to be implemented because for the technological complexity, and we have to address the problem of the interoperability between fiber and free space links. So, for example, the choice of the wavelength to be used is quite natural. So we have to move to 1550 nanometers, and the idea is also to develop compact and portable devices that can be ready to be deployed in a actual infrastructure. So the development of our prototype started from the definition, the design of a new scheme that can be useful for realizing a quantum key distribution transmitter that must be a state generator able to produce at least 3 states from 2 mutually unbiased bases. So, for example, the state H and V and the diagonal one, or the other states. But the important thing is that they must be from 2 mutually unbiased bases. So the idea here of the Pontiac state encoder is to combine polarization with a interferometric configuration that is based on the Sagnac interferometer. So, for example, in this scheme, we enter with a diagonal polarization into a fiber-based PBS, that is this one in the middle of the figure, and then from the PBS it started a Sagnac interferometer with one delay line in one arm, and in the upper part you can see a phase modulator, okay? And so the PBS split the superposition between the two horizontal and vertical polarization and produces at the end of the propagation through the Sagnac loop a superposition between these two states that are modulated by the phase modulator. And in particular, the smart thing about this new scheme here is that the polarization through the Sagnac loop is always aligned with respect to the slow axis of the fiber. So, for example, both the components of the light passes through the phase modulator with the same alignment, and so this scheme intrinsically does not suffer from problems in which we have to enter into the phase modulator with a diagonal polarization. Okay, so for example, in the bottom you see the results that we obtain with these first prototypes that works at 800 nanometer. We obtain a Q-bar of about 1%, okay, for a test that lasted for about 30 minutes. So this was only the first proof of concept for this scheme. And then we introduced another another method that we use in our prototypes, that is asynchronization techniques for quantum key distribution that does not require to use external signals like sharing optical signals or using other synchronization techniques. So, for example, the ones based on the use of the GPS signal in order to synchronize the two terminals. Okay, and so this qubit for sync algorithm allows us to synchronize, so to implement all the necessary steps involved in the full implementation of the BB84 quantum key distribution protocol without adding complexity to the system, because we use directly the qubits which are exchanged in the protocols. Okay, so these are the two novelties that he introduced in 2019, and then we tested the two together in a first implementation. In this first implementation, we realized a QKD transmitter based on the Pognac configuration, and with the use also of an intensity modulator, we actually were able to produce the three polarized state and the two levels of intensity that are necessary to implement the protocols. Then we send these states to a quantum channel made up of a fiber spool of about 26 kilometers, and then we add also a variable optical attenuator in order to test the system under different conditions. And at the Bob side, we implement a standard polarization measurement with two PBS in which the setting of the basis is made but by two automatic polarization controllers that in real time, by using some bits that are some states that are predetermined between Alice and Bob, Bob can synchronize in real time with Alice and also use the information about this fixed sequence that is sent to him in order to compensate for the polarization fluctuation that there are in the channels. And then the detection here is performed by using 4 SNSPDs. You can see here the results, for example, obtained in a run of 45 minutes in order to check the Q-bar that we can achieve, okay? And the Q-bar that we achieve here is extremely low, okay? It is actually the record low Q-bar reported in literature, and so it is about 0.05%, okay? And also we test the system in a longer run, okay? So for 6 hours we check that both the synchronization and the polarization compensation algorithm worked in our implementation. And then we changed the setting of the channel in order to stress our system, and we show that we can tolerate up to like 23 dB of channel losses. Okay, and also all the analysis is performed also by taking into account the finite size effect in the estimation of the secret key rate. Then we introduce a first improvement in this Pognac scheme, because actually in the original scheme we have to manually check the polarization that enters the PBS of the Sagnac interferometer, and this can be a problem from the point of view of an automatic implementation, okay, in the field. And so we introduced this new version of the Pognac, that is the improved Pognac or iPognac, in which the single mode fiber before the PBS is replaced by a polarizing maintaining fiber, and the beam splitter that realize the superposition between the two horizontal and vertical polarization is actually in free space, and with this replacement, actually this scheme results auto-compensating, because here, even if the polarization maintaining fiber introduce a phase shift between the two components, this is actually auto-compensated at the end of the cycle. And so this augments the stability of the source, and so we manage to realize a sort of calibration that lasts for more hours, okay, and also the results of the Kubert was really good and better than the previous version. And so we also test this Hyponiac implementation in a first field trial that was realized in our university network. We realized a fiber link of about 3.4 kilometers through our university network using a dedicated deployed fiber. Okay, so we bring our boxes that at that time was 2 boxes, one that fit for the optical part, in particular the size of a 2U. So you see here in the bottom part with the letter B the box of Alice, and in the letter C there is the box of Bob, that is actually a box with due to size, but in this scheme we use 4 detectors that are INGAS based detectors that occupy some spaces, okay, and so and also we choose to use 4 detectors in order to augment the possible secret key rate obtainable in the realization. So this was the first field trial that we realized, and then we also realized another trial. So this was based on the Hyponiac configuration, so in order to how to compensate for the calibration, but there is also another alternative, that is to use an automatic polarization controller in the input of the Poniac encoder. Okay, so we also tested this other scheme in another realization, in which actually we use only 1 fiber to transmit both the quantum and the classical communication. These tests were realized last year between June and July, okay, and we actually have these new boxes here that are 4U boxes that contains all the systems, so the PC, all the optics, especially in Alice, and in the side of Bob we decided to improve the system by using only 1 detector. Okay, so there is a new detection scheme that is based on the time multiplexing of the signals that allows us to use only 1 detector. And so now we have this sort of portable system that can be really deployed in a fiber infrastructure. And we test our system in a link of about 13 kilometers, and these are the results that we obtain. So the Kubert of about 2% and the secret key rate of about 1.67 kilobits per second. And what about free space? Because also free space is essential in the vision of a global quantum communication or quantum key distribution infrastructure. Free space at the moment cannot compete with its fiber-based counterpart, but we can some way formulate some key requirements that free space quantum communication must fulfill in order to be compatible with the fiber-based infrastructure. So, for example, we require the full day functionality and the compatibility in wavelength with fiber-based system, and also to obtain this, we have to couple the free space signal into a single mode fiber. And we realized in the last years a first free space prototype for quantum key distribution at 1550 nanometer in daylight in free space that was called QCOSONE. This was a project funded by the Italian Space Agency, and this prototype was exploited also silicon photonics to realize the transmitter. So here we have no Cognac or iCognac, but it is a single chip realizing the polarization and intensity modulation that are required to implement the BB84 protocol. And we tested our prototype, in which we also develop all the point acquisition and tracking system needed to effectively inject the light into the single mode fiber. This is based on the correction of the low order aberrations introduced by the atmospheric turbulence, okay, by using an active feedback on a movable fast steering mirror that corrects for the angle of arrival of the incoming beam. And with this system, we managed to have a coupling efficiency on average of about 4 or 5%, and this was quite enough to implement the full measurement of the impolarization of the states by exploiting a system that is similar to the one that I showed before. And we implemented this prototype, this free space prototype, in a link of about 145 meters between the department and the location of the laboratories. And we actually managed to show that the Q-bar that we obtained was very low and was also very stable. So we managed to exchange key also with the sun at its maximum elevation. That is the situation in which the atmospheric conditions are the worst for free space quantum communication. And so also working at 1550, we managed to reduce the background to the sun, because we can exploit all the mature filter, very narrow filter that we have that are available for telecom application. And these are the results. So we show that for 3 consecutive days we managed to obtain QKD in daylight after 1550. But also this was only the first prototypes, and then in the recent months we developed 2 different prototypes that can be attached to the boxes that we developed, and these prototypes are 2, one transmitter, 1 receiver, that realize only the optical pointing between the 2 terminals, so they are responsible of the effectiveness of the free space channel. And these systems are things to be used as a portable system to be implemented in links up to 1 kilometer. And the test that we performed in a urban environment here in Padua between the Department of Physics and our department show that it is possible to run QKD with our boxes also in free space by exploiting these free space prototypes that we developed. And so the idea for it to create a real test bed in Padua that show the interoperability between fiber links and free space links, okay? And the next steps are also that we are working with the Italian Space Agency towards the realization of satellite QKD at 1550 nanometer. And so HASI started a big project called High QKD, in which the goal is to develop a satellite dedicated to quantum communication. And this fits very well with our expertise in the context of satellite quantum communication that started in the 2010, like with the Italian Space Agency, and we show in the various years the feasibility of using different encoding for satellite quantum communication. We implemented also some fundamental tests of quantum mechanics, like the Wheeler-Delay's choice experiment, and we show also that orbits like the one of the GNSS satellites are also viable for quantum communication with discrete variables. And in the last years, we concentrated on the development of optical ground station, for example, in Matera and in Padua. In Matera, in particular, thanks to the collaboration with the Chinese group, we performed some QKD exchange with the Michio satellites, and here we can see an example of the improvement that we reached. That, for example, in the first implementation, the point accuracy of the ground station with respect to the satellite was about 50 microd. So we work on the improvement of this fine point acquisition and tracking system, and we managed to obtain now at the moment a precision of about 5 microd, and this is quite enough to allow for an efficient coupling into the detector for the QKD exchange. And we are trying to repeat all these steps also in Padua, where we.
Francesco, can you try to speed up, please?
No, I finished. Okay, so this is the last slide. We are trying to implement also this free space technology and optical technology in Padua, where we have a new telescope of about 40 centimeters, and the study that we started was aimed at realize some satellite tracking, like the one of the International Space Station that it is shown here. Okay, so this actually ends the presentation. This is only the list of the collaborators, and this is the list of the references to the works.
Thank you very much for a nice talk and nice review on your activity on quantum key distribution in Padua. I don't see a question on YouTube, but maybe we wait just a few seconds because we have a delay. And okay, I'm sorry, you have been a bit long on the talk, so the time for discussion is somehow compressed, and we have to go on to the next speaker. It is Alessandro.
Okay, thank you.
Thank you very much, Francesco. Okay, so please, Alessandro, can you switch on your camera and try to share your presentation? Alessandro Candeloro from Milan on the properties of asymptotic incompatibility measured in multi-parameter quantum estimation. Alessandro, are you there? Okay.
Can you hear me?
Sure.
Can you?
Perfect.
Can you?
Yes.
Okay, fine. Yes, I had a problem right now in that moment, so but should be
Try
so.
to be strictly 20 minutes, and then we have time for discussion.
Okay, I will try. So I share my screen, so you should see.
Yes.
My presentation here. So now let's try to put in presentation mode. Okay, can you see it?
Perfect.
Perfect. Okay, fine. Thanks.
You can go.
So good morning. Okay, thanks. So good morning, everybody. I'm Alessandro Candeloro, PhD student at University of Milan, and I would like to thank the organizer to let me present this new work I developed with my supervisor Matteo Paris and Marco Genoni on the properties of asymptotic incompatibility measure in the setting of multi-parameter quantum estimation. So just a brief outline of the talk. What we did was to find upper bound on the maximum number of compatible parameters and to study this recently introduced asymptotic compatibility measure in the full estimation of qubit system. I will introduce all the technicalities in my talk to let you understand what is about. And so let's start by studying what is multi-parameter quantum metrology. In general, the information about some parameters is encoded in a quantum statistical model, so in a density matrix. And the usual way to extract information is by performing some measurements that are described by POVM. And the distribution probability of the outcomes depend, of course, on the values of these parameters. And how much information is encoded in this probability distribution is quantified by the Fisher information matrix. And the well-known result in classical estimation theory is the well-known Kramer-Rao bound, where the covariance matrix of any unbiased estimator is lower bounded by the inverse of this Fisher information matrix, where M is the number of times we repeat the experiment. When we move to multi-parameter quantum metrology, we can also derive more restrictive and measurement-independent bound by introducing the SLD operator, the symmetric logarithmic derivative operator, which is implicitly defined in this way. And from that, we can define a new matrix, the SLD QFE FI matrix. From that, we obtain a new bound, which is measurement independent in the sense that it doesn't depend on a specific measurement scheme. And the first question that arises, of course, if this bound is attainable. And in the single parameter case, the answer is yes, this can be attained by performing the optimal POVM composed by the projectors over the eigenstates of this SLD operator. When we move to the multi-parameter case, so when P is larger than 1, then this bound is not in general on a table, and heuristically we can understand this by considering the most simple multi-parameter case, P equal to 2. Then, as we said, to the first parameter correspond an optimal measurement given by this corresponding SLD operator, and the same for the second parameter. But if these two measurements doesn't commute, then the optimal strategy for estimating the first parameter will be not optimal for the second one, and vice versa. So how we can compare these two strategies? Well, the first thing would be to consider the corresponding Fisher information and for each optimal strategy. But the problem is that Fisher information are only partial ordered. So we couldn't say if one is better than other by looking only at the matrix. And for this reason, scalar bounds have been introduced, and there are different ways to introduce scalar bound. And in this talk, we consider the one that relies on the introduction of a weight matrix that, as the name says, weight differently the importance of parameter. And so by taking a trace of the weight matrix times the quantum Fisher information, we obtain the corresponding scalar bound and the corresponding inequality. And for the same reason we mentioned before, this is generally not attainable. We can also define a more theoretical most informative single copy bound in this fashion way, but it's quite difficult to find results in general by directly minimization on all the possible POVMs. Another important bound, which will be clear why it's important in the following, is the Olevo-Kramer-Rao bound. This has a particularly cumbersome definition and is also hard to evaluate in closed formula in general. Some results are known, like for qubit and Gaussian systems. Nonetheless, the numerical minimization of this, the definition relies on a numerical minimization, and is known this minimization is a semi-definite problem. But why this Olevo bound is important? Well, it's important because in the asymptotic model where we have n copies of the systems, and we allow measurement on these n copies, and this measurement might also be collective measurement, then the most informative bound in the large n limit is equal to the Olevo bound. So the Olevo bound is the most informative bound on this asymptotic model for n that goes to infinity, and for measurement that might also be collective measurement. So as we said before, the optimal strategies for individual might not be optimal for the joint estimation of all the parameters. And this can also be quantified by what is known in literature as the Ullmann matrix. And this is nothing but the average of the commutator of the SLD operator corresponding to the alpha and beta parameter. And by introducing that matrix, we can upper bound the Olevo bound by the scalar bound itself. Indeed, we know that the Olevo bound is larger, since it's most informative than the SLD scalar bound. But this is also, then it was proved that this Olevo bound is also upper bound by the scalar bound, SLD scalar bound itself, by a factor of 2. And this inequality can be put also more restrictive by introducing this asymptotic incompatibility measure, where this means that we take the largest eigenvalue of this matrix, where this is the SLD quantum efficient information matrix, and due the Ullmann matrix we define here. So some properties of these asymptotic incompatibility measures, well, is lower bounded by 0 and upper bounded by 1, as we can easily understand from these inequalities. And if this quantity is 0, then the Olevo bound coincides with the SLT scalar bound for all the weight matrix. And we say that in this case, the model is asymptotically a classical model, since the calculation of the Olevo bound is much simplified and correspond to the SLD scalar bound. In this case, the corresponding parameter, we call them asymptotic compatible parameters. Indeed, the real quantity we should look for to see how much the Olevo and the scalar SLD bound difference is this renormalized difference. However, the problem of this difference is that depends directly on the weight matrix, while the asymptotic incompatibility measure is W independent. So this is much more easy to calculate and characterize in general the quantum statistical model under study. And moreover, this quantity is invariant under reparameterization, and this will be an important properties in the following. So if we change the parameters in our model, then the asymptotic incompatibility is the same. So this was just the introduction to explain the technical things. Let's now move to the new results we derived from this new recently introduced asymptotic incompatibility measure. And so we start by considering the problem of the maximum number of asymptotic compatible parameters. So far, only the largest eigenvalues of the compatibility matrix have been considered. But we may ask also, what is the role of this matrix that we saw on with incompatibility matrix? To do so, we introduce a mathematical theorem known in literature as the Cauchy-Interloss theorem. So we consider an n times n Hermitian matrix and an n minus times n minus principal submatrix. That means that we have this matrix, and we just raise the second column on the second row, for instance, and then we obtain this corresponding matrix. Then the eigenvalues of A and the eigenvalues of B, put in decreasing order, interlast each other, in the sense that the largest eigenvalue of A upper bound the largest eigenvalue of B, which upper bound the second largest eigenvalue of A, and so on. This is particularly useful for us because if we consider a quantum statistical model with a set of P parameters, and any other possible submodel defined by a set of possible reparameterized P minus 1 parameters, then the asymptotic incompatibility of the largest quantum statistical model upper bounds the asymptotic incompatibility of the submodel, which is again lower bounded by the second largest eigenvalue of the incompatibility matrix. And from that, it easily follows that we can upper bound the number of maximal compatible parameters if we denote by delta the number of strictly positive eigenvalues of this incompatibility matrix. Then the quantum statistical model contains a maximum number of compatible parameters equal to p minus delta. And this can be easily shown by just recursively apply the Cauchy-Interlast theorem to the incompatibility matrix, because we have shown that this holds. And if we consider, again, a p minus 2 submodel, and we apply the same argument, we can upper bound the asymptotic incompatibility of this p minus 2 submodel with the asymptotic incompatibility of the general model and the third largest eigenvalues of the incompatibility matrix. Then, if we recursively apply this argument, what we found is that the asymptotic incompatibility for the p minus j submodel is lower bounded by these eigenvalues of the incompatibility matrix. But if j equal to delta, then these values might be 0, and so the asymptotic incompatibility might be 0. So there might be compatible parameters, compatibility. And so for this reason, the maximum number of compatible parameters might be equal to this value. So let's now move to study the asymptotic compatibility measure for the full tomography of quantum finite system with finite dimensional Hilbert space. In general, we can write this state in terms of Cartesian coordinates, where these sigma j are the generators of the Lie algebra SUD, and a general state here can be represented by d squared minus 1 parameters. Then the asymptotic incompatibility for a qubit is easily derived, and we can see that depends only on the purity of the system. And we were also able to derive the asymptotic incompatibility for single-mode Gaussian states defined in this way. And again, we see that this asymptotic incompatibility is in one-to-one correspondence with the purity of the system only. So we ask ourselves if this is true also for a general d-dimensional system with d larger than 2. So the problem was that we were not able to derive analytical results by just looking at the states and evaluating the SLD operator. So what we did to gain some insights was to just random generate states and solve for each random states the Lyapunov equation that find us the SLD operator. And from that, we can derive the SLD, quantum Fisher, and Newman matrices. And eventually, we can numerically evaluate these asymptotic incompatibility measures. And what we obtain is that, so we see that the asymptotic incompatibility is no longer a one-to-one function with the purity, mu, but the asymptotic incompatibility relies on this area. And we did this for d equal 3, 4, and 5. So oops, it's not work. Okay. So since we know that the asymptotic incompatibility measure doesn't depend on the parameterization we are considering, we just try to see if we can derive some more analytical results by looking at another parameterization, which is known in literature as exponential coordinates. So general quantum density matrix, d-dimensional quantum density matrix, can be expressed in this way, where H is this sum of, again, the generator of SUD algebra. And we have also introduced this beta, which is a fictitious temperature that allows us to normalize these values, and is just is not a real parameter of the model. And so, again, we had some difficulties in deriving analytical result, but we look at a simple case. So at diagonal H. In this case, the asymptotic incompatibility is exactly the analytically derivable and is equal to the hyperbolic tangent of beta times delta m divided by 2, where this delta m is the difference between the maximum and minimum eigenvalues of H. Remark, this is not a submodel in the sense that we are neglecting the estimation of some parameters, but we are just setting some parameters equal to 0 to simplify the calculations. And we see that by changing this h in the exponential coordinates, we see that all these lines represent the asymptotic incompatibility for fixed h, and we see that these lines span all the region for the asymptotic incompatibility. So the next step was to understand how this change if we have non-diagonal density matrix. So we again randomly generated quantum density matrix. We evaluated the beta and delta m for each random state, and we numerically again evaluate the asymptotic incompatibility, and we compare what we found numerically with the results obtained with diagonal states. And what we found is that they always match, at least for d equal 3, 4, and 5. We see that these always match, and this happened also for the eigenstates of the incompatibility matrix for this full tomography of quantum finite system. So what we did is that we conjectured that this expression holds for any finite dimensional system and also for non-diagonal system, where beta and delta m are can be derived by diagonalize the quantum density matrix. And this is consistent with the qubit formula, since there is a one-to-one correspondence between the purity and this product delta m. And remarkably, this holds also for single-mode Gaussian states. If we write the purity as a function of n and as a function of beta omega, then we can write this relation also for single-mode Gaussian states. And also, by looking at the eigenvalues of the incompatibility matrix, we were able, since we can conjecture that this is the representation of the eigenstates of this matrix, we were able to count the strictly positive number of eigenvalues. And so we were able also to conjecture that the maximum number of compatible parameters in the full tomography of quantum system with a finite dimension depends only on the dimension d, and d is equal to this quantity. Okay, so just to conclude, these are the three main results. We found a general criteria to estimate the maximum number of compatible parameters, and this is the formula. And we also conjectured this true for the full estimation of finite quantum system on of dimension d. Future perspectives are just to mention this study more in detail this bound and understand if it's saturated or not, also in other cases, not only in the full tomography of quantum finite system. And we also would like to develop more tools to study multi-parameter problems that may not be addressable in analytic formula, and eventually also study the role of noise parameters and their effect on the quantum methodological incompatibility, and it's also on this maximum number of compatible parameters. And so this was all, and I'm open to questions.
Thank you very much, Alessandro. I have a small question while we wait for the gap with the YouTube transmission. Is it possible to extend this to continuous variable systems?
What do you mean continuous variable? I mean, for Gaussian, this.
Right.
Yes. So we did something about that. Let me just move on. I just don't know why I asked. So we did, but not where is okay. So for single mode Gaussian system, we were able to derive all the important matrix I mentioned, so the quantum Fisher information matrix, the Ullmann matrix, and the incompatibility, and as I said, asymptotic and maximum number of compatible parameters. And in general, for continuous variable system, the problem is how you should parameterize this kind of system with a finite number of parameters. So for single mode, it's okay, but for a general continuous variable quantum system, I'm not sure, because I mean the results, especially the one on the maximum number of compatible parameters, relies on matrix relation, so finite dimensional matrix.
For Gaussian state, you probably may use the covariance matrix as a representation of the density matrix itself.
Sure, yeah.
Okay, thank you. I don't think there are no questions on the YouTube chat. I encourage people to address questions to the speakers through the chat. It's the only way during this online part of the conference to interact with each other. So please address your question with no problem. Don't think that it are stupid, the question, because any question can be an increment of the comprehension for everybody. Thank you very much, Alessandro. And we move to Alessia Levi from Como. Alessia, can you hear me? Can you switch on your camera and share your screen?
Okay, so let me try to share the screen. Okay.
So you have 20 minutes, and then we have a few minutes for discussion.
Okay, is it okay?
Yeah, sure.
Okay, so I can start. Okay. Sure. So thanks, Alberto, for the introduction. My name is Alessia Levi, and I work at University of Insubria. And today I want to present an experimental work that we realized here in collaboration with Maria Bondani from CNR. The topic of my work is the characterization of the robustness of mesoscopic twin beam states propagating through noisy and lossy channels for quantum communication protocols. So the motivation of our work is connected to quantum communication, and even if this is a preliminary study, so quantum communication has received a lot of attention in the last decade since the seminal paper published in 1992 by Bennett and Brassard. For instance, as Francesco mentioned before, in 2017, Chinese people used the Mencius telescope to realize the first entanglement distribution between two places 1,200 kilometers apart. Usually, quantum communication is realized at the single photon level by using direct detection schemes that employ single photon detectors, and information is encoded in the states by using the different degrees of freedom of single photon states, such as polarization, path, momentum, time beam, orbital angular momentum, and so on. But actually, some years ago, there was a different proposal, a different approach. In 2002, Grossan and Granger proposed to use a different apparatus to perform quantum key distribution that employs homodyne detection instead of direct detection employing a single photon detectors, and information is encoded in continuous variables instead of discrete variables. So this was a different proposal, and many experiments have been realized since then. So now I want to move further and present our idea. So our idea is a third alternative, and since we have a long-standing expertise in dealing with mesoscopic states of light, we want to use mesoscopic twin beam states of light that are entangled in the number of photons, and these twin beam states are characterized by a multimode thermal distributions. The detection scheme is a direct one, but instead of using single photon detectors, here we are employing photon number resolving detectors that are detectors that can count the number of photons contained in each laser pulse. So in particular, in this work, we used two hybrid photodetectors produced by Yamamatsu that are commercial photon number resolving detectors operated at room temperature. And essentially, these are composed of a photocathode followed by an avalanche diode operated below breakdown threshold. So these detectors are endowed with partial photon number resolving capability and have a good linearity up to 100 photons. But the question is, are these mesoscopic states of light that we want to detect and characterize by means of photon number resolving detectors good enough, and are they robust enough against losses and noise sources? In order to investigate this point, we need a non-classicality criterion that can be testify the presence of entanglement, and in particular, it's important to notice that this criterion can be should be easily accessible. The important thing is that it can be written in terms of measurable quantities. And to this aim, we use the noise reduction factor that is a sufficient criterion for entanglement, because it can be easily written in terms of measurable quantities. In particular, in our case, with our detectors, we have access to the number of detected photons. So the noise reduction factor can be expressed in terms of the number of detected photons. And in particular, we can find an analytic expression for the multimode twin beam state that I presented in the previous slide. So what to do? First of all, I just want to mention some previous work of ours in which we investigated the robustness against losses. In particular, we considered as a loss a possible imbalance between the two arms, between signal and idler, in such a way that the noise reduction factor can be expressed in this simple form, and T here represents the transmission efficiency in the idler arm by assuming that this is a further this is a sort of inverse of the loss. So if the transmission efficiency is equal to 1, it means that the signal and idler are perfectly balanced. If t is equal to 0, it means that we are completely losing the idler. So by using this expression, we were able to testify the robustness of our twin beam states in the presence of a loss statistically distributed, because we consider three cases that are the uniform distribution, Gaussian distribution, and long normal distribution of this transmittance efficiency. So every time you measure the noise reduction factor lower than 1, we can certify that the correlation are subshot noise, and so they are non-classical. Okay, now I go to the main goal of our work, that is to consider the possibility to have some noise sources superimposed to the twin beam. So in this case, the noise reduction factor can be written in the presence of these noise sources. Here I'm assuming that both the arms, both signal and idler, are affected by this noise. And what we can see is that at variance with the previous expression of noise reduction factor here, in this case, we have a fourth term that is formed by the information that contains the information about the noise sources. In particular, it contains the mean value and the variance of the noise in each of the two arms. In particular, we can notice that this term can be positive, negative, or even equal to 0 according to the statistics of the noise sources. In this work, I'm particularly interested in the case in which only one arm, I will say the idler arm, is affected by this noise source. This is the case in which Alice produces the entangled state and then sends to Bob one portion of this twin beam state. So she keeps the signal and she sends the idler. And so we are assuming that only the idler arm is affected by a noise that can be added in the transmission channel. We can also consider the presence of the imbalance between signal and idler so that we can have this expression that is analytic in which both losses and noise are included. And now I want to show you the results that you obtained in 3 paradigmatic cases that are a coherent noise source, a pseudo-thermal noise source, and a Fox state noise source. These are paradigmatic because coherent noise is described by a Poissonian statistics. So in this case, all the moments are equal. And in particular, this means that the variance is equal to the mean value. And so in this case, for coherent noise source, there is no fourth term. So the presence of noise is only in the denominator of the second and third term. And in particular, here I just want to investigate for which conditions the noise reduction factor is less than 1, and so for which conditions we can measure subshot noise correlations. And what we can discover is that this condition doesn't depend on the mean value of noise. So there's no threshold involving the mean value of noise. The only condition that we found is concerning the transmittance efficiency, so the presence of an imbalance between signal and idler. And in particular, we can measure non-classical correlation when this transmittance efficiency is between T1 and 1, where T1 has this expression, it is essentially the smallest solution of this second order equation. So for the values that we used in our experiment, the value of T1 is around 0.05. So in the case of a very strong imbalance between signal and idler. Let me go further and let me consider the case of a pseudo-thermal noise. In this case, we have a super Poissonian statistics. And in this case, we can notice that we have the fourth term in the noise reduction factor that can be detrimental for the measurement of non-classical correlation. In particular, we can notice that this term depends on the mean value of noise and on the mean number, the number of modes of the noise source, that in principle could be equal to 1, but it could be also a multi-mode thermal distribution, and in this case the effect is less detrimental than in the case of mu equal to 1. So in this case we have non-classical correlation every time the mean value of noise satisfies this inequality. So in particular we have a threshold on the mean value of noise, and it depends on the mean number of photons per mode of the twin beam state, and it also depends on the presence of an imbalance between signal and idler. Finally, I want to present the case of a Fox state noise. It is quite strange to have a Fox state in the transmission channel, but it can be added, for instance, by some eavesdropper in order to change the information sent to Bob. So it could be possible. In this case, we have a fourth term that is negative. And in particular, if we investigate the case of non-classical correlation, we found this threshold condition. Actually, this threshold condition is always satisfied for values of the transmittance efficiency between T1 and 1. In particular, for T equal to 1, the presence of a Fox state doesn't change the non-classicality level, as it is shown in the red surface. And we just want to mention that also in this case, we can recognize the same condition that we found in the case of coherent noise and thermal noise, that is the condition regarding the transmittance efficiency. So now let me present the experimental results, because I promised that it is an experimental work. So here we want to test our theoretical model, and to do this we produced twin beam states by sending the fourth harmonic of a neodymium laser operated at 500 Hertz into a beta barium borate crystal. So the twin beam state is generated at frequency degeneracy, and the two portions are spatially and spectrally selected and delivered to the hybrid photodetectors that I presented before. So first of all, let me consider the case of a coherent state. In order to prepare the coherent noise, we use the second harmonic of the laser because it is at the same frequency as the twin beam, that is in the green region, at 523 nanometer. And so this signal was superimposed to one arm of the twin beam. And in particular, we performed two kinds of investigations. So we measure the noise reduction factor as the mean value, as a function of the mean value of noise for a fixed mean value of twin beam, and the noise reduction factor as a function of the mean value of twin beam for a fixed mean value of noise. So let me go to the experimental results. Data are shown as dots, while the colored curves are the theoretical expectation according to the model that I presented before. And in particular, we can notice that we have an excellent agreement between experiment and theory. And in particular, I just want to mention that these theoretical curves are fitting functions. And so from the fitting procedure, we can obtain information about either the twin beam state or the noise source, and we can also obtain information about the detection chain, so about the quantum efficiency, the global quantum efficiency, and the transmittance efficiency. We did the same in the case of a quasi-single mode thermal state that was obtained by sending the second harmonic of our laser to a rotating ground glass disk and selecting a single speckle by means of a pinhole. We performed the two kinds of investigation as in the case of coherent state. So the noise reduction factor as the mean value, as a function of the mean value of noise for a fixed mean value of twin beam, and as a function of the mean value of twin beam for a fixed mean value of noise. And also in this case, we obtained very good agreement between theory and experiment. And also in this case, we were able to obtain information about the twin beam state, the noise source, and the detection chain. So let me summarize the results. We developed a comprehensive theoretical model to take into account the presence of losses and noise sources in the quantification of non-classical correlations, and the non-classicality was expressed in terms of measurable quantities, and the experimental data are in excellent agreement with this theoretical model. In particular, we observed that the more super-Poissonian the noise, the more detrimental the effect of noise. In particular, coherent noise doesn't determine a threshold on non-classicality, while in the case of a pseudo-thermal noise, we should keep the mean value of noise as low as possible in order to observe non-classical correlation. Finally, we noticed that in the case of a Fock state, for a perfectly balanced condition between signal and idler, the presence of the Fock state doesn't change the amount of non-classicality. So for what concerns future perspectives, now we are trying to further test the robustness of twin beam states in a more realistic condition. In particular, I just want to mention the possibility to increase the mean value of our twin beam states by using proper photon number resolving detectors like silicon photomultipliers that have a larger dynamic range with respect to hybrid photodetectors. Finally, the possibility to extract information about the noise from the noise reduction factor suggests the implementation of new communication channels. For instance, the information can be encoded in the noise superimposed to the twin beam, and the losses mimic an eavesdropper interference. Thanks for your attention.
Thank you very much, Alessia, for the nice talk. I just have one question while we wait if someone writes questions on YouTube chat. I mean, as far as I understood, you have used the value of the detection efficiency independently from the transmission value. Is this, I mean, connected to some measurement, or just it's a technical data on the detectors that you use for the detection efficiency?
No, actually, I just, it's an important point, because actually, if we look at the datasheet of the detector has a quantum efficiency that is around 0.5, so around 50%. But actually, what we are measuring here is the global detection efficiency of the entire detection chain, so including losses due to the use of optical multimode fibers or of a lens and filters and so on. So this is a global detection efficiency that we extracted by using the theoretical model and fitting the data with this theoretical model.
Okay. Okay, thank you very much. There is one question on the chat. Is there a way to experimentally measure or estimate the asymmetric losses in signal and idle paths? It's Martina Esposito asking.
Mm-hmm. Yes, no, this is mainly more focused on the first work that I presented, that is in the first part of my presentation, where we tested our model by really changing this transmittance efficiency in one arm of the idler, and in this case we were able just to focus on this transmittance efficiency, and we were able to prove the value of this transmittance efficiency. So the model is general. It can be focused on only on transmittance efficiency if you are sure that you don't have additional noise sources, and so it's quite robust. Of course, if you have many parameters, it's difficult to keep all of them under control, but if you just focus on one or two, you can properly estimate the parameters themselves. You have different ways to check if these parameters are properly estimated, because you can measure the loss independently, for instance, by considering the mean value, and so you can know what is the expected value.
Thank you very much. So we come back at 11:20, and we will start again with Martin Delgado from Madrid for his keynote talk. So thank you very much to all the speakers of this session. And if you like to send us your presentation, we can then share with the participants to the conference. Thank you very much.
Okay. Good morning.
Good morning.
Oh,
Shall I present?
I cannot hear. Sorry. Okay. Okay. Now I can hear.
Oh, no, sorry. I will use my earphones. So.
Okay. So it's a pleasure for me to chair this session, and the first speaker of this session is Professor Miguel Ángel Martín Delgado, that will introduce us to his talk at QFold, a quantum metropolis optimization algorithms. So please.
Okay, thank you. Can you hear me well, and can you see my presentation?
Yes, we can hear.
Okay, very good. Thank you. So first of all, I am very happy and I'm pleased to participate in this Italian Quantum Information Science Conference in the 13th edition. And the topic I will be discussing is QFold, which is a quantum metropolis optimization algorithm. These are my coordinates, and I want to thank the organizers of this IKIS edition for the invitation. I also want to thank my collaborators, Paulo Casares and Roberto Campos from Universidad Complutense, who must be also in the audience. And this is the reference I will be discussing in this presentation. I will skip this, some sponsors I have to show. Okay, the summary briefly is, after some preliminaries, I will introduce this QFold algorithm as a hybrid quantum classical algorithm, and then perform quantum software classical simulation to validate and test this new hybrid algorithm, with also some quantum hardware simulation in the IBM quantum machine with minimal cases. And I will end up with some conclusions and outlook. So the preliminary, in order to motivate this study, is the fact that we are interested in searching for new quantum algorithms. And the reason is the real potential of quantum computers is still unknown. And most likely it will remain unknown until we build them, actually. This is what happened in the past with classical computers, and also with the transistor, and also with the laser. There were many applications that could not be foreseen beforehand. And I believe this is the same case with the quantum computers. But then, in this situation, we have to motivate why we should build a quantum computer, giving some hints and examples of interesting quantum algorithms that go beyond the initial set of quantum algorithms, like they are here. These are purely quantum algorithms, are very scarce. Examples of these are, in the 90s, the Deutsch-Joseph-Simon, and also later Shor and Grover. The first two were just academic, without no use, and the Shor and Grover, they were really useful. But we want to expand the range of possible interesting quantum algorithm. One interesting case of also this purely quantum algorithm is the H8L algorithm for solving linear equation, which opens many ways to incorporate these linear solving algorithms in other problems like linear, differential equations and many other optimization problems. But these are purely quantum algorithms, and what I want to highlight is that purely quantum algorithms do not exist from the fundamental point of view, because there is always a classical part. There is always a measurement, and measurement means classical data. So we have typically to classical preprocessing or post-processing the information around a quantum computer, right? So if we have this observation, it is natural also to raise the importance of the classical information part in quantum computation and try to put them on equal footing and see how they can help each other. And this is the idea of a hybrid algorithms, meaning quantum plus classical. So in this diagram, I just picture a classical computer that receives classical input data, and when it has to make a computation, which is very hard, it calls for quantum operation, and they are transferred to a quantum computer. It does these quantum operations, which are hard, and it returns classical values because of this measurement to the classical computer. The classical computer works with binary programs, and the quantum machine with quantum states. After this, the classical computer will output a classical result, which is the one we are searching for. Examples of these hybrid algorithms are very popular. A very popular one is the quantum eigensolver that was introduced for typically quantum chemistry, in which you have a classical computer that does the optimization part, whereas the quantum computer does the calculation and the preparation of the states and measurement of correlators, which are very difficult to compute in a classical computer. The outcome of this iteration between the classical computer and the quantum computer is the molecular spectra, for instance, which is very useful for designing drugs or materials. So this is a typical example of a hybrid quantum algorithm, and this will enlarge the list of quantum algorithms towards instances in which they have practical application and not just academic. Typical examples that we can address with this hybrid quantum algorithm are the optimization problems, either theoretically or with industrial applications. And the optimization problems are interesting for quantum big computers because they are typical instances of hard problems for classical computers. They need large state space to find the solution, and classically it is necessary to visit one by one state. Quantumly, we can profit for doing that in superposition with quantum parallelism. So natural setting to apply quantum algorithms with hybrid versions is these optimization problems. Examples of quantum algorithms, there are now many, there are many advances, and I want just to mention two of them that we did in our group with Pablo Casares. One is a quantum version for linear programming, which is something very, very useful in optimization. And we were able to introduce a quantum version of the interior point predictor corrector algorithm, which is the best algorithm in classical linear programming. And we found quantum advantage with respect to the typical parameters governing the behavior of these problems. We also have another instance of this hybrid algorithm for quantum active learning, for sampling against adversarial attacks, which are very destabilizing attacks for algorithms like finding pattern matchings with active learning. This is something that can be mitigated with this quantum hybrid algorithm. Now, in optimization problems, typically the generic, the abstract setup is that we have states and transition. The states corresponds to the defining problems, and the transition are the moves from the state to one state to another state. And this corresponds graphically to a graph. This is a network of nodes and links representing states and transition. And the goal is for the optimization is to minimize or optimize a fitness or a cost function or reward function. This is the typical setup for optimization problems, and some examples are here on the right. One very typical example is the Trebelman sales problem, and this is an example with Turin, Spanish cities, and the problem is to find this. This is the cost function here. The fitness function would be the length, the kilometers you spend in order to visit all the cities. Now, the optimization problem I am interested in this talk is the one of to predict the three-dimensional structure of proteins. And I will tell you why, and I will just start by reminding you about some basic of these proteins. The basic building block are the 20 amino acids, like this one, the alanine. And with that, you can build composite of these amino acids that are called peptides, the proteins that they start growing with 2 peptides here on the left, or 9 peptides, the oxytocin on the right, and so on and so forth. Now, the problem of the three-dimensional structure of the proteins means that you have to be able to characterize, to see what is the position of these atoms in the three-dimensional space. And for that, what the biochemist uses is the torsion angles. These torsion angles, like these phi outside in the picture, they are dihedral angles that they can tell you what is the angle between planes crossing the bonds in the molecules. You have then a set of torsion angles, and with that information, you can reproduce in three-dimensional space what is the orientation of each bond in the molecule of the protein. So this is the data. So the states in the optimization problem that I said before correspond to angles, rotation angles. The problem is a bit more complicated. There are side chain effects, so we need extra angles in order to have a better representation of these in some part of the proteins, but these are details that can be accommodated later on. And also, it is known from studies in protein studies that there is a structure. It is a well-known structure of the proteins called the secondary structure instead of helixes, called alpha helixes here on the left, or seeds, these beta seeds here. So there is a knowledge of a characterization of some common parts that the protein have. But the problem of having the precise three-dimensional structure of a given protein is really something very difficult, and this is the subject for biochemistry. Now, why protein structure prediction is important and very hard? Well, it is, if you know the three-dimensional structure, you know the function, you know what you can do with your protein, you know how it is arranged in three-dimensional space. Now, it is hard, yes, because it is a combinatorial problem. You play with the distortion angles, the phi and psi, and you make all possible combinations. You easily see that it grows exponentially. So it's the typical case in which you to have some quantum processor could be beneficial. And it is also hard from the point of view of the experimental methods. They are very expensive, they are complicated, you can make errors, and they are time consuming. So these experimental methods like X-ray crystallography, fluorescence spectroscopy, etc., it takes a lot of time to produce the three-dimensional structure from a crystallized version of the protein. So it is interesting to have some software to predict this atomic structure in 3 dimensions and benefit from the functionality that you may obtain from that information. Now, before entering in quantum algorithms, they are very good, but they have very interesting improvements in classical approaches. One is based on metropolis hasting and simulated annealing approach, which is called the project Rosetta. This Rosetta project, what we will try to do with QFOL is the quantum version of this Rosetta project. More recently, there are deep learning approaches like AlphaFold of DeepMind, and they predict very good structure, very good schemes of folding of the proteins, which are very accurate. And we will also incorporate these deep learning approaches into our hybrid quantum algorithm that we call QFOL. So this is the precedent. Now, let me introduce then the quantum version, this QFOL, this hybrid quantum classical algorithm. First thing is that even though AlphaFold 2 has recently been proven to be extremely effective, find this very close solution to the ground state, there are still open problems to deal with. One is that there is a huge gap between known proteins in a database and the real list of folded proteins, actually 3 orders of magnitude. So it means that you have to still many work to do in order to take the huge list of proteins and find their real expression in 3-dimensional space. There is also something that is called dark proteome. This is the dark side of the proteins. They are proteins that they have not been able to be crystallized or find their structure. They We know they exist even in the human body, but they are inaccessible for doing these experiments. So it would be interesting to find out about this. This is important because AlphaFold 2 has not proven this dark proteome, and as it is a deep learning algorithm, it has bias. So it's interesting to see whether we can test other algorithms which are less biased. Also, there are proteins with several stable foldings, so not unique folding, and this is a complication, how to deal with that. And moreover, there are intrinsically disordered proteins with intricate dynamics, so it's very difficult to predict the structure. So there is room for improvement for introducing quantum algorithms in these hybrid versions. The idea is taken from these classical random walks used by Rosetta project, the classical Metropolis Hastings algorithm. The idea is that you start with a configuration of the rotation angles and start moving these angles, and by accepting or rejecting the angles according to the Metropolis algorithm, you eventually find a finish at the outcome of a folded protein. Now the point is that you can repeat this several times in order to see which one gives you the lowest energy, and it's the most probable configuration. Now, in doing so, you see that you have to repeat many times this classical algorithm. And what we propose with the quantum random walks is, in this pictorial view, is to take the rotation angle into a quantum register and explore in parallel all the configuration space for these quantum quantum states, encoding these rotation angles and performing quantum operation in order to enhance the probability of finding this minimum energy configuration, which will be at the end the folded protein. So we expect to be faster and more efficient in doing quantum version of these random walks than with the classical walks. But this is something that we have to test. So this is just a simple recollection of what a random walk does. It's a process to explore a state of the space with random movements. And this is done classically. I will tell you how to do it quantumly. So the classical Metropolis algorithm, this is just for completeness. This is the algorithm in which you start with an initialization with a random point. In this case, it will be a random set of rotation angles, and you have a generation function for obtaining new candidates. You apply the criteria of Metropolis, and eventually you accept or reject, and then you start moving, creating this random walk. Eventually, what you want to explore is a probability distribution pi, of which you only know the Boltzmann factors, but not the normalization factor. So this is why this acceptance ratio is you don't need all the information about the distribution pi. Actually, this is provided with a version called the simulated annealing, in which what you do is to make the acceptance value dependent on a temperature parameter T, and this simulated annealing reduces the system energy until the minimum is reached. Like here, in this case, you see that you run the algorithm until eventually you have a scheduling for reducing the temperature, this parameter. Eventually you reach a maximum in this case, or equally for a minimum. We will do this quantumly. So with quantum walks, the whole space is visited in a superposition of states. This is what I mentioned before, and this is what I compare here. This is the classical path on the left, and these are the multiple paths visited all at the same time, and making the process more efficient. Now, what is the underlying structure behind these quantum walks? This is something technical. I will just make a summary to give you an idea of the ingredients that we use in order to obtain a quantum algorithms, starting with the idea of the Grover algorithm, the quantum search algorithm. The quantum search algorithm is an algorithm for doing quantum amplitude amplification based on two reflections that combine produces a rotation, and by applying that rotation several times, you reach a maximum, and that's where you obtain the data you are looking for, in this case, the optimization problem. Well, that algorithm was extended into the realm of quantum walks by Szegedy, and in this situation, you have a graph representing nodes, representing the states, and the leaks correspond to the moves, the transitions, and the classical metropolis algorithm is encoded in some transition amplitudes called Wij, and these are embedded into the quantum register and the operation of quantum unitaries. Here they are called U and B, and this corresponds to these reflection and rotations. Well, there's some technical points, but the idea is that one is doing a sort of Grover algorithm in a more expanded quantum register space, and motivated by this acceptance or rejection rates of the corresponding underlying classical algorithm, but now classical metropolis, but now embedded into this quantum walk of Szegedy time. Eventually, one applies several walks W, which are unitary, from 1 to say L. These are L-step quantum walk, and this gives you a quantum state afterwards. And this is the one that you use in order to predict whether the maximum or the minimum is obtained in each situation for the optimization process. Now, the Q-fold uses this quantum Szegedy random walk and combines recent deep learning advances with the well-known technique of quantum walks applied to this metropolis algorithm. And importantly, it is a fully scalable hybrid quantum algorithm. We will do simulation for smaller scales, but it is fully scalable. It does not require a lattice model simplification, which is something which is more popular in the market of protein folding. And it corresponds to a realistic parameterization in terms of torsion angles of amino acids, the realistic variables that use deep learning techniques, classical deep learning techniques, or Rosetta, the Rosetta algorithm. We find an incipient polynomial quantum advantage when compared with classical analogs, both for different schedule and fixing the schedule. And finally, we perform a simple, minimal proof of concept of the quantum metropolis algorithm in IBM quantum hardware. So the global scheme of the Q-fold is a string of amino acids, a featureless string of amino acids that it is prepared in an initializer with some preprocessing, and then it is fed into the quantum metropolis and provided some auxiliary library, an oracle that provides you energy, calculates energy needed in order to do the process, the optimization process. Eventually, at the outcome, it produces the folded protein, the guess of the protein when it is folded in 3 dimensions. This flow chart shows the previous scheme, but more detailed. This initialization model that you see here, you can choose between randomization of the rotation angle or the one that appears after running a mini-fold version of the AlphaFold classical algorithm, and then well, the parts correspond. Either you want to have a quantum hardware simulation or a classical simulation on the right. We will show later on. So other approaches to quantum protein folding, they mostly rely on adiabatic algorithms like D-Wave, and they use this lattice model, which is an oversimplified treatment of the problem. The advantages of these simplified versions, they allow us to simulate larger peptides, but the problem is that they are not very realistic. They do not use the same parameter as the real software, classical software, and they do not quantify the quantum advantage. And this is the two things we are going to obtain with Q-fold. Now, before doing that, we need to define a figure of merit when looking for a metric to assess the goodness of given solution to protein structure prediction. This is something that we need in order to test whether our algorithm is good enough compared to classical ones. And in doing so, we have to make a balance between what we want. We want a model that with high probability finds the correct solution, And at the same time, we want such a procedure to be very fast. Now, both things you cannot have because, for example, going through all configuration solution would be quite accurate, but extremely costly. So we have to make something balance between both options. And this is something which is achieved with a metric that is called the TTS, for total time into solution. And this is the expected time that it would take to find the correct folding, and combines the increased probability with the required number of steps. The number of steps is T here in this formula. Delta is a success, success probability that is fixed beforehand. We use the common choice of 0.9. And PDT is the probability of hitting the right state after those steps in each attempt. PDT can be computed classically by running the classical metropolis several times, or quantumly by the amplitude in the quantum case. This can be classical probability or quantum probability, depending on whether you're using the random classical or random quantum network. Now, how do we use this TTS? Well, we had to find the minimum TTS, signaling that we have achieved the situation in which the algorithm finds the folded structure of the protein. In this, on the left, in this red case, you see that increasing the states, you see that TTS increases. So this is a situation you don't like. You want to find a minimum. On the green side, you see a case in which the TTS decreases. This is good, but you have to find a minimum. You have to keep on decreasing. And in this orange case, you see that the TTS decreases and then increases. So this means that at step 2, this value 20.63 would be the minimum TTS. And these are the values we will be computing either with a classical metropolis or with a quantum metropolis. We have made some tests beforehand in order to see whether the initialization of the rotation angles, either done randomly or by using a deep learning method like this minifold, we want to see whether the precision corresponds to a better precision with the minifold and better performance with the minifold as compared to the random choice of the rotation angles. And we see that when the peptides are tripeptides, tetrapeptides, we see that the precision of the minifold is better than the random choice of rotation angles. And similarly, the minimum quantum TTS with the minifold choice, running the minifold as the initialization module, is better than just doing randomly. Compare the values. These are lower than this one on the left. So how do we test the goodness of this quantum version of the metropolis algorithms? How do we test? We have to compare the behavior of this figure of merit, this TTS, the quantum minimum with the classical minimum, and then if we have this plot in which we plot quantum TTS versus classical TTS, we will see a region in which the classical is better and one region in which the classical is worse. So we have to find out with our data running a classical simulation. We have to find out a scaling law and see whether the exponent, the scaling exponent, and the prefactor, the overhead, fits with respect to the main diagonal of this plot. So the worst case in which is when we are in the upper part of the diagonal, not only the overhead but also the scaling exponent. And the best case in which it is when you are fully below. This one here is something worse because you start good, but then you go to the worst region. In our case, we will see that because of the limited resources that we have in the classical simulator, we start with some in the region in which it is worse, but the scaling law points towards the region in which there is a quantum advantage. And this is the first time that we find that the quantum advantage can be found in the protein folding problem. These are simulations that we have done with QuizKit run in the platform of Amazon Web Services. These are the plots with the quantum TTS versus the classical TTS, the minimum cases. And the important thing is that in red, we plot the initialization with Minifold, the deep learning, and in blue with the random initialization. And we run several cases of dipeptide, tripeptide, tetrapeptides, and different precision for the rotation angles measured by beats. And at the end, what we found is a scaling law that tells you how this quantum TTS is compared with the classical TTS. And the important thing here is the exponent has to be less than 1 in order to have a quantum advantage, and the prefactor has to be over 1. This is with doing the scheduling with a fixed beta, as I said before, for the classical annealing. This is, but we can do variable beta result, some sort of quantum annealing, and we use different schedule: logarithmic, linear, exponential, and geometric. We found that the geometric one gives you the best behavior of the exponent and the prefactor, with a quantum advantage. And whereas, for instance, the exponential gives you nothing, no advantage. So it is important. So this is an important message. It is this classical simulation with quantum software in classical machines. It is important because there are cases, there are algorithms which are heuristics, like this quantum hybrid, that you cannot predict beforehand which is going to be the quantum advantage. It's not like in the Shor algorithm, the global algorithm, that you can make analytical calculation and say, okay, this is it. I know that there is a quantum advantage beforehand, before running the program in a real quantum computer. There are other algorithms like this one, based on quantum metropolis, in which you need to do an experiment, and a virtual experiment, in order to decide whether or not there is an advantage. And this has to be done because there is an heuristic about how you run the schedule of varying this parameter, the temperature. So what does these plots mean? Well, they means that, for instance, if we have a precision of 6 rotation beats, which is very similar to the one that AlphaFold uses, and we consider an average protein of 250 amino acids, and assuming an exponent like before of 0.89, we find that we can get 80 order of magnitude difference in the TTS between the classical and the quantum. So it means that we would have a real quantum advantage. Finally, we have done also small experiments with quantum hardware. In the previous case, we were using classical simulators, and they correspond to noiseless, the ideal functioning of a quantum computer. Here, in this case, we go to the real quantum machine, the IBM Cube, and we consider a minimal case of 8 dipeptides, several dipeptides. Actually, we consider 8 cases. We take only 2 rotation angles, only 1 bit each, and only 2 quantum walks, which is the minimum quantum walks you need in order to have interference, coherence. And we want to see whether this coherence is beneficial with respect to doing it with purely classical. Well, we have adapted this quantum metropolis algorithm of the Q-fold using this Szegedi random walk, quantum walk, to the geometry, to the circuit of IBM Cube, and we have to do a lot of optimization. These are the register with the moves, with the states. These are they are registered with the oracles, registered with the operation of the unitaries in the quantum Szegedi quantum walk. This is something that is explained in the 10-hour paper. But the final result is the following. In this plot, we have the big plot is the experiment result with quantum hardware in this IBM quantum for 8 dipeptides, and we compare the difference. This is the difference between the probability of choosing beta equals 0, which correspond to infinite temperature, meaning that all the states are equally probable, and we don't have any optimization problem whatsoever. And running the algorithm between beta 0.1 and 1. And this difference, if it is positive, it means that doing and scheduling with the quantum computer is beneficial with respect to doing nothing. Actually, in this I am finishing. In this inset here, we have the theoretical result with the same machine, with the Qiskit Qiskit software in the IBM with the same, and we see that in this dash line corresponds to the situation in which beta is 0, temperature infinity. So the probability of every state is 1/4. And the fact that these probabilities are above this horizontal line means that the Q-fold is beneficial, because the effects, the quantum effects, produces a success probability which is higher than the classical case, right? So when we do this with the real quantum hardware, we have this data with this error bar, because we run this experiment many thousands of times, and we see that there is an agreement between the theoretical prediction with the quantum software of the Qiskit and the quantum hardware of the same machine, this Casablanca machine in IBM. There is one anomalous point here for this dipeptide, in which there is no advantage, but it is 1 out of 8. We don't know the real reason for that, but it could be that it is a malfunction of the quantum hardware. Sometimes the machine does not work well, because the prediction of the machine, the ideal prediction of the machine, is this one in green, and it tells you that there is always an advantage. Anyway, it is interesting to see that a minimal realization of this Q-fold with the IBM quantum hardware is able to see this enhancement of the optimization problem by means of quantum resources. So the conclusion, just to conclude, we have to study how quantum computing may complement modern machine learning techniques to predict the structure of proteins. Q-fold is an algorithm that implements a quantum metropolis using as a starting guess, the output of a machine learning algorithm. So it combines these two algorithms. Q-fold is also a quantum algorithm that is able to incorporate all reality details common in classical algorithms. This is it is a new unique feature, and it is the first to measure hints of quantum advantage in protein structure prediction in terms of these torsion angles, which are the realistic parameterization. And finally, we have run a proof of concept, a small implementation of Q-fold in actual quantum software. But I want to finish with the following conclusion. It is very interesting and very important to run quantum software simulation in classical computers, because now there is a lot of effort devoted to find application of NISQ computers, these near-term quantum computers, which are very noisy. These are the ones we have right now available, and we are very much interested to see what we can do. But it's going to be difficult to obtain real, very good, useful application for that, a real quantum advantage in the sense of something practical. Now, what we can do is with quantum software and running in classical computer is to find out, like here we have done with Q-fold, to predict which algorithms, which hybrid algorithms could present a quantum advantage. And this is something that you have to do the experiment, the virtual experiment in your classical computer, and decide whether this algorithm could be advantageous or not. And this is something that calls for these virtual experiments, and this is another line of study which is worth pursuing, and this is one of the motivations with our study. So now we are generalizing this Q-fold to something that we call quantum metropolis solver, in order to address not just protein folding problem, but also artificial intelligence problems, finance problems, and other optimization problems. And with this, I finish by thanking again my collaborators, Pablo Casares and Roberto Campos from Madrid University, in Complutense University in Madrid. And this is it for now. Many thanks for your attention.
Okay, thank you for your very nice talk. And it's time for questions. Well, there is a small delay with the
okay.
The
I'm not seeing the YouTube channel, so you have to tell me. You have to tell me.
there is a small delay. There are no questions on the YouTube right now. Maybe I can ask something and we see if something happens on the YouTube. Well, my question is, as far as I understand, the protein fold problem it consists in finding the minimal energy of a very hard energy landscape. And classically, it can be done using thermal annealing, for instance. But you do with this quantum walk that you implement with your quantum metropolis. So my question is, there is a quantum equivalent to this thermal annealing, that is quantum annealing. Did you try to compare your approach with quantum annealing?
Well, what we did is, my answer is no. But what we do is a quantum metropolis version of this quantum annealing by means of this Szegedi quantum walk. So what we do is take a random walk, classical, parameterized with these transition amplitudes, the W probabilities, the transition probabilities, and embed it into a quantum walk. And then we make this, we consider this as a fair comparison. Now, what you propose is something else, which is also very interesting, but we didn't. So it could happen that there is a better way to do this quantum metropolis. There is a better way to introduce quantum effects in metropolis by means of this quantum annealing in the problem of protein folding. But we haven't done it. We have done something that it looks quite parallel. I mean,
okay,
there is a way that you have a Markov chain, and you make a quantum version of the Markov chain. This is what we have done.
Okay. Okay. Thank you for your answer. Let's see if there are questions. No. So there are no questions on YouTube. So I really thank Professor Delgado, and I move to the next speaker.
Thank you.
Thank you. So the next speaker is Filippo Caruso.
Hi.
That will give a talk about quantum machine learning.
Yes. Can you see my slide?
Yes, yes. So you have 20 minutes and a few minutes for discussion.
Okay, so good morning to everybody. And first, let me thank the organizers for this opportunity. I will talk on quantum machine learning. So I work in Florence, and where you have a quantum hub for quantum technologies involving several institutions, not only the University of Florence, but also Lens and CNR, and also in close collaboration with IRIM in Turin. And in my group, we are working on several activities, theoretical activities, going from open quantum systems to optimal control, and from quantum sensing biosystem to quantum transport. And in the last years, we have been working also on quantum machine learning. All these activities are theoretical, but often in close collaboration with experimentalists. So as you know, I mean, as we already had about during this week, and machine learning is a set of tools to give the computer system the ability to learn something. Like you can classify data if you have some labeled data sets, and it's called supervised learning. You can have unlabeled data sets, so you want to go for pattern recognition, and it's what is called unsupervised learning, or enforcement learning, where you have some agent taking action in some environment to maximize some reward, as you had from Valeria on Monday morning. And of course, this machine learning is, as you know, is useful in our everyday life, going from domotic systems to autonomous cars, from speech or voice recognition to medical diagnostics. And you can go from machine learning to quantum machine learning, replacing bits with qubits, and of course running classical quantum algorithms on the quantum machine. And then preserve, of course, these applications that I was discussing before that you have from classical machine learning. And this looks to be the next big challenge, especially because first, these NISQ devices or this quantum hardware is becoming more and more available with more and more qubits. And also because we have the software, because as you know, for instance, last year, Google has released TensorFlow Quantum. This is a quantum version of the library TensorFlow, that is the main open source software library for machine learning. And under this umbrella of quantum machine learning, I like to make this distinction depending on the type of data you have and the type of algorithm you're running. So if the data can be either classical or quantum, and also the algorithm can be either classical or quantum. So if you have a classical data and classical algorithm, so CC, let's say here, this picture, then is the classical machine learning. You might have a classical machine learning applied to quantum data, as was discussed, for instance, by Martin Delgado in his very nice talk just before me, and it's called QC. Or you might have a classical data, but quantum algorithm, so running on a quantum computer. And finally, let's say the fully quantum machine learning scenario, where both the data and the algorithm are quantum, so QQ, quantum machine learning. And let's start now. I would like to give an overview of our recent results in these areas, let's say in QC, in CQ and QQ subfields. And so QC means, as I said, the quantum data and the classic algorithm. That, in my opinion, is the simplest task here. And we started from a toy model that is like a quantum walk on a complex network, as it was discussed before me. And so we have a complex network graph with some adjacency matrix, this matrix A here, but you have also some noise. So like for instance, the coupling rates, the link weights are given by stochastic process with some probability distribution as described here. And what we want to do is to classify such noise. You can have different types of Markovian noise. We have Markovian versus non-Markovian. And in order to classify such noise, what you want to do is to avoid any control path, because it might be very challenging from the experimental side, and we don't want to measure any coherence, any entanglement, but we just measure node populations. So the populations for each node of the graph at different time steps. Well, if you apply a list of several machine learning algorithms like subtree vector machine, multi-layer perceptron, or recurrent neural networks, what we found is that you can get an accuracy above 97% for non-Markovian noise classification. And in addition, we realized that if the noise is time correlated, it's better to use the recurrent neural networks, RNN, that are usually indeed exploited for time correlated data, like for speech recognition or text recognition. And okay, here this is the model for these recurrent neural networks, and on the top right side you can see the table where we compare several machine learning algorithms, and the numbers are the accuracy in percentage. And indeed, it seems to work very well. But this was a toy model. So the next step was, let's apply it into a real device. And like to this noise intermediate scale quantum device that Miguel has mentioned before me. And here the goal was, okay, let's try to see if there is some noise fingerprint associated to each device. Of course, before running your algorithm, you should know which type of noise you have in your simulation, your real quantum device, and possibly you can take it into account during your simulation and during your quantum hybrid classical quantum algorithm. So in this here, you can see a quantum circuit that is mimicking a quantum walk, as described before. And then the goal is to discriminate between two different NISQ devices by using binary classification models, in particular subtree vector machine, that is a supervised learning model where you want to map data from some input space into a feature space where you can find some hyperplane to classify this data in a linear way. And this is called embedding or classical embedding. And so we have considered several real quantum devices provided by IBM Q. And we have repeated we have run the same circuit many times, also in different days. And this is what we got. As you know, these NISQ devices by IBM have different names like Athens, Bogota, Casablanca that Miguel has mentioned before, or Lima, Quito, Santiago, and so on. And basically, if you take any pair of devices, it's always possible with an accuracy of 100% to distinguish them, to say, okay, look, what you have running, of course, the same circuit, the same quantum circuits. I can tell you on which machine you have run it. And this also is very robust. So if you repeat it, you get similar results, and it's also time independent. Even if you take the same machine, like this Casablanca that has already been mentioned, if you consider Casablanca and you repeat the same quantum sequence in different time steps, what we found is that after a time scale of about 4 or 5 hours, the noise fingerprint does change. So you can distinguish what Casablanca is doing now between from what Casablanca will do in 5 hours, because the noise is changing like every 4 or 5 hours according to our observations. And now let's go to the other another, let's say, area. What is this umbrella here? That is CQ, so classical data and quantum algorithm. So like you can generalize the classical embedding I was discussing to the quantum case. You can have classical data like these red and blue blocks that you want to map in the feature space. That can be the Hilbert space that, as you know, is exponentially growing in size. So why not? And this is like is the block sphere, if you consider a qubit. The goal is to embed all these red and blue, let's say, cubes into this in 2 regions in such a way you can divide them in a linear way. So within a plane, for instance, in the case of the block sphere. So like class A and class B. This can be done by using a cost function that has to be minimized. So in particular, you want to maximize the overlap in the same class. That's why you have a minus sign in front. And you want to minimize the overlap between different classes. And this can be measured by the so-called Gram matrix that contains all possible, the square modulus, all possible scalar products. In order to map the data from the input space into the feature space, you can use a quantum sequence, what is called a quantum feature map. And this has been proposed by Seth Lloyd and Maria Schud and other co-workers in this MIT Xanadu collaboration. So you have like classical images, you can embed them by using classical neural networks into some some input x1 and x2, and then in this quantum circuit you have some parameters. You have several rotations and also some control rotations, some 2-qubit rotations, and well, these x1 and x2 appear in some rotation along the around the x-axis, and in addition, for some other rotations like the one around the y-axis, you have some free parameters, some control parameters, something that you will optimize during this process. And at the end of the circuit, you have a state. And this is the state, the quantum state that you want to, at the end, have in this, let's say, in 2 separate regions. And well, starting from this inspired by this work, what we did was to further exploit this theoretical scheme and then test it experimentally. And in particular, we have explored several platforms, experimental platforms, let's say, that in our opinion are complemented in some respect. We went from ultra cold atoms on atom chips with these atomic platforms in Francesco Cataldiotti's lab in Florence, to a photonic platform in Marco Barbieri's group in Rome, and also we have exploited superconducting qubits by using here the Righetti device that is available via cloud. And here you can see what happens. Okay, what you get before learning. Before learning in the block sphere, you can see that like this, your data point in random directions. The problem that we are addressing here is that you have, as you can see in the top left side, the top left corner, you have this 1D data, blue and red, that are, let's say, in this way, as you can see, and we want to classify them. We want to put in one side all the blue ones and on the other side all the red ones by using this quantum embedding. So before learning, so when you have random parameters in these quantum circuits, the block vectors point in random directions, as we can see here. After learning, as you can see the theoretical results, indeed you can get these 2 families of data, A and B, and that are clustered, as you know, as we expect, as we want to find by minimizing such cost function. And indeed, it works very well also for the experimental side, as you can see with atoms, or with superconducting qubits, or with photons. And in the bottom line, you can see in this 3D plot the gram matrix. That is where you want to have a diagonal matrix in the so the identity in the diagonal blocks, because we have class A and class B. You want to have clustered families of data, and then you want to have 0 in the off diagonal blocks where you have the overlap, because you want to have that these clusters are far apart from each other. And once you have these quantum states, you can make quantum state homography. You can apply some POVM to distinguish them, but you might get also here inspired by artificial neural networks that this is called deep learning, where you want to have all the input layers, hidden layers, some output layer. You want to classify images. But here what you are classifying is classical information. What happens if you are dealing with quantum information like quantum states? And indeed, by exploring a very simple graph and the dynamics of a quantum walk, actually here is a noisy quantum walk or stochastic quantum walk, what we found is that the probability of successfully discriminating between two non-orthogonal quantum states very quickly in time goes to the so-called Estron bound or level Estron bound. It is the best that you can do by quantum mechanics. In addition, if your walk in this graph is noisy, so if there is noise, you get more robustness. And of course, in all these applications that also were discussed before me, the robustness is very important. You want to have your results have to be robust again with respect to any imperfection in the topology, in the state preparation, and so on and so forth. So then we have this work was done together with my former postdoc Nicola Dalla Pozza last year, and then now we are testing it experimentally by using by running the quantum walk on an optical network in Paolo Maddaloni's group, where we are demonstrating experimentally what we found before theoretically, and in addition we are proposing a new approach for multi-state quantum discrimination based on the arrival time degrees of freedom. And finally, I would like to discuss two examples of quantum machine learning. The first one is reinforcement learning. As you already heard on Monday, the idea is to find some real-time optimal strategy with higher reward. And here we got inspired by our previous work that in collaboration with Fabio Sciarrini and Roberto Sellame, where we studied the dynamics on a quantum maze, on a noisy quantum maze. And then we realized that the escaping probability from a maze, the maze is a typical paradigmatic problem in this context also for reinforcement learning. But here we just studied the transport dynamics, and we found that the escaping probability is like when the walker is a bit quantum and a bit classical, so it's a bit noisy quantum walker, the escaping probability that you can see in this plot on the y-axis is 5 or 6 orders of miles higher than what you get in the purely quantum case or in the purely classical random walk case. As also was discussed before me in this Grover search algorithm, usually with quantum walk you have a quadratic speed up, like on a chain. You might have exponential speed up for some topologies, like for glued trees, but here, by exploring this stochastic quantum walk dynamics in presence of some noise, we got an exponential speed up. So inspired by this, going back to reinforcement learning, also here the typical problem is the paradigmatic problem is the so-called is when you have like a mouse escaping from a maze, or actually finding some piece of cheese in some environment, in some maze topology. And this is the typical reinforcement learning problem. It's the more paradigmatic model. You have an agent performing an action in some environment, then the agent that is in that case is the mouse, is getting information from the environment, so observations and also some reward from the environment, and based on the agent will perform the next action. And this will repeat several times until the agent finds the optimal strategy, like at this point I have to go to the right, then to the left, and so on and so forth. Of course, the environment is indeed a maze, and since you have an agent moving on an environment, what we thought, and this was the main new contribution from our work, was to rephrase the reinforcement learning into the quantum domain in terms of the open quantum system framework. And so the walker is quantum, the agent is quantum, and of course we cannot, while the mouse make discrete steps, here everything is quantum, so it's delocalized. And the effective way we found to mimic the actions of the mouse in the maze here is given in terms of some action on the adjacency matrix. So basically what the walker is doing, what the agent is doing, is to like break some wall, creating some shortcuts to find to quickly find the exit site, or creating a wall. So the opposite action is that one. And everything is quantum, but it's also noises, because we consider this quantum, this stochastic quantum walk model. And this is what we found in this picture here, in this 3D plot. You can see the final reward as a function of time and as a function of p. P is an interpolating parameter going from 0 when you have a purely quantum walk model to P1 where you have a classical random walk. In between, you have what is usually called the stochastic quantum walk. The surface is what you get without optimization, without reinforcement learning, and the colored dots are what you get after the optimization, after running this reinforcement learning algorithm. And in addition, what we found is that if the quantum agents are noisy, everything is more robust. So the noisy quantum agents are more robust for reinforcement learning. And well, now let's go to a final example of quantum machine learning. And this is related to what is called the generative adversarial network. What is that? Well, you have two, it's like a game, you have two players. One is called the generator and the other one discriminator. You start from some real data, some images. The generator during his turn has to create some fake image. And on the other side, the discriminator has to discriminate between the real image and the fake one. Then the next turn, the generator will make a better fake image to make the job of the discriminator more challenging. And if the strategy spaces are convex and compact, it's possible to show that this game ends when you get a unique Nash fixed point that corresponds to the situation that the fake image is equal to the real image. Of course, the generator has not access to the real image, but at the end of the process, is making a fake image that is essentially the same as the real one. This is called a generative adversarial network, or simply with the acronym GAN, or GANs. And what was done by, in this other still MIT Xanadu collaboration, is Physics Review Letters 3 years ago, is to generalize this model to the quantum case. They generalized this model and they conclude the papers. Of course, they analyze several configurations. The real and fake data can be the classical quantum. The discriminator, the generator can be the classical quantum. And then they conclude the paper saying, if you have classical data, so the real data are classical, high dimensional, and if both the discriminator and the generator are quantum, so they are using, both of them are using quantum computers, then they say that you can potentially get exponential speedups over the classical generative adversarial networks. What we did in our work was to see it in practice. So because here they introduced these new Q-GANs, but the question was, can we do it in practice? How do we implement these Q-GANs? So first, you need to explain how the discriminator generator makes such quantum states, because of course now we are talking about quantum states instead of classical images. And here, what we did was to use parameterized quantum circuits where we have some unity maps depending on some free parameters, θ1, θ2, θ3, as I described before for the quantum embedding work. Then you apply measurements. You want to minimize some cost function, and you need to repeat these things several times. You have several iterations until the process is optimized. And this work was done in collaboration with my colleague in Florence, Leonardo Banchi, and the real work was done by our PhD student Paolo Braccio. What our focus was to understand, let's say the convergent behavior of such training process. Because of course, before training it in practice, in the real quantum computer, real quantum hardware, you want to be sure that it's really working, it's really converging. And this is not obvious. And indeed, what we found is that if your states are pure, so we have pure quantum information, noiseless quantum information, this works very well. But if your quantum information is noisy, so like mixed states, you end up in these limit cycles. So there is no convergence. As I can show you in this animation, the black dot is the initial fake quantum state. The red one is the real quantum state. Of course, the game should end or should converge when the black one is on top of the red one. But if you use gradient descent optimizers, or even the best performing optimization algorithm in machine learning, it is called ADAM, based on some first, second order moment estimation, for those who are familiar with that. And what you find is that there is no convergence. You have really a problem here. The game does not end as we expect, because we have this limit cycle. So what we did was to propose a new strategy based on optimistic mirror descent method. The idea essentially is that each player does.
Sorry, you have just a couple of minutes more.
Yeah, I'm finishing. You have just a couple. You have just each player has to try to guess the opponent's move in order to improve his strategy. And indeed, if you do that, it works very well. You get convergence that is also very fast, as you can get with this method, with this strategy. So really quickly, the fake state overlaps with the real quantum state. Then, just to conclude, you can go from quantum state to quantum channels, or quantum map, or quantum circuits, or quantum operations, as and now what we are proposing is a new framework that we have called super QGANs, that that basically discriminate between quantum channels. The quantum channels can be something like the quantum communication channels, or noisy quantum circuits. Okay, so the goal here, as you can see from the title, is to perform quantum noise sensing by generating fake noise. It's possible to demonstrate that any noise can be closely approximated as a Pauli noise channel, where you have Pauli rotations with this index k. When k is 0 is the identity, k1 is sigma x, k2 sigma y, k3 is sigma z. And if what we did was to find P of, the goal is to find P of k. Is to find the P of k, your fake noise is equal as you estimate the noise channel, the quantum map. So here you can see in blue that these histograms are the probability distribution, the discrete probability distribution P of k. P of k is for the target, for the real noise. QK is what you generate by what is called fake noise. And indeed, the distribution are very similar. Of course, this also holds for quantum metrology, because of course our framework is proposed for any type of quantum channel. The Pauli noise channel is just an example, and it can be even a more general random unitary channel. And if the probability distribution is a delta function, and you have this unitary matrix here, you are dealing with the Mach-Zehnder like interferometer. So you have like a quantum phase estimation algorithm, and the goal is to estimate some parameter S, some phase S, with m bit precision with n probes. And indeed, you have this kind of scaling between n and m. And this is a particular application. Of course, the noise can be also correlated in space on time. You have the circuits with some auxiliary. We have here, as you can see on the bottom right side, we have measurement qubits, environmental qubits, system qubits, and ancillary qubits. Some initialization map. Then phi here is the real or the fake quantum channel that you want to discriminate. And then you have a measurement map. In the top, you can see what you use for spatial noise correlations. In the bottom, you can see a map D that is probing your system at different time steps. And this is a scheme by which you can exploit noise temporal correlations and non-Markovian noise. And just quickly, you can, for instance, in the spatial noise correlation case, it works very well. And in particular, you can take as an example the the two-use memory channel proposed by Chiara Machiavelli and Massimo Palma 19 years ago. This is one of the first, or probably the first one example of quantum memory channel. And indeed, if you plot the Kullback-Leibler divergence between the two distributions, PK and QK, as a function of this correlation parameter mu, what you see is that if the generator is able to generate correlated channels, this divergence remains close to zero. If the generator can make only non-correlated channels, non-correlated in Pauli noise, then the divergence increases as a function of mu. If you look at the probability distribution of PK and QK, as you can see, there's a very good agreement between the target distribution corresponding to the real noise and the generated distribution corresponding to the fake noise that you are generating. Similarly for the temporal noise correlations. So just to conclude, the take-home messages are that since if you want to run a hybrid classical quantum algorithm, as was described very nicely before me, it can be really crucial to also to estimate, characterize, quantify, and even possibly fix the noise in these NISQ devices, since we are still very far from fault tolerance quantum computing. So we have to deal with this noise in these devices. And you can do quantum embedding even if your devices are noisy, as we did moving from theory to experiment in the other work. You can discriminate between quantum states by using optical networks, and then in a fully quantum machine learning scenario, we have introduced a new framework based on open quantum systems for quantum reinforcement learning, and also we have proposed a new model that we have called super QGANs to sense noise by generating fake noise. And of course, all of these might find very promising applications, as we have partially did with some experiments or some tests in real quantum devices. For this can be useful, as I was saying, for quantum computation or quantum communication or for quantum sensing. And this was an overview over several works we did in the last year. And if you want to know many more details, you can have a look at this reference. So thank you for your attention. If you're interested in any postdoc position in quantum information science, please contact me, especially if you want to work in quantum machine learning. The team will be also supported by this new European project for the next 4 years, where I'm coordinating the Italian participation. So with this, I would like to thank you again, and really here for answering to your questions. Thank you.
Okay. Thank you for your very nice talk. Well, we are a bit long with time, so maybe there is time for just one quick question.
Yes.
There is no question from the web. Well, if there is no question, I have a very quick question, actually a curiosity. Well, if I understood correctly about random walk, you claim that hybrid quantum classical strategies outperforms either quantum or classical.
Yeah, this also.
Can you give some physical simple argument for this result? Because we have something similar in quantum assisted, in classical assisted quantum annealing, but this is a rather different context.
So the intuition, but this is something very old that apart from this paper, is also inspired by previous work we did when I was working with Martin Plano in Germany, and on noise-assisted transport for light harvesting system for quantum biology. And there we realized that if you have an interplay between the noise and quantum coherence, you get speed up. And there are several ways to understand it, and to get an intuition, we can think that because of the coherence, you get like parallel computation, like so. And but then on the other side, thanks to the noise, you can reduce some destructive or constructive interference in order to find, let's say, the optimal strategy. So let's say the geodetic towards the exit side. And so this can be the phrase also in terms of broadening and hopping rates in some n-level, two-level system. But the point is that indeed somehow you are playing with destructive and constructive interference, and thanks to the noise, you can destroy pathways that are very slow.
Okay.
This is more or less the intuition, but if you want more interested, we can discuss later during the lunch break or later.
Okay, Okay, there are no more questions from the web, so I thank the speaker and I would move to the next one. Alessandro Romito.
Thank you. Bye-bye.
Bye, Filippo. Alessandro Romito give a talk on measurement-induced topological entanglement transition in a free fermion model. Ciao, Alessandro.
Ciao. Can you hear me?
Yes.
I'm sharing my screen. Can you see my screen?
Okay, now yes. So you have 20 minutes plus 5 minutes for questions.
Please come closer to the microphone.
Can you hear me?
Yes, but the voice is not very loud, so please come closer to the microphone. Thank you.
Is it better now?
Yes.
Okay. So first of all, I would like to thank the organizer for putting together this very nice meeting. It's been very nice to see you meet in person in the past days. Unfortunately, I'm still stuck in the virtual world for a little bit. This talk I would like to present today concerns many-body systems in their dynamics in and out of equilibrium settings, where the out of equilibrium is obtained via quantum measurements. The results I present are partially published and partially new results which should be out in the coming days. And most of what I will present has been obtained in collaboration with Graham Kells from Dublin City University and Galit Maidan from Ben Gurion University of Negev. So our starting point is the entanglement properties of many-body systems. This has been already discussed in at least a couple of previous talks in the previous days. The quantity we're looking at is the entanglement entropy, which is the von Neumann entropy of a subset A of a bigger system. And we have seen already in the previous talks how the scaling properties of this entanglement entropy determine the properties of the system. So we have volume law or area law scaling, depending on whether the scaling is extensive with the size of the region A, or whether it's scales with the size of the border of region A. So when you look at low energy physics, this different scaling distinguish gapped from critical or gapless system. When you look at states which have finite energy densities, this concerns thermalization. The typical situation is the one in which the system, due to a given Hamiltonian, has eigenstates which scale like with volume law scaling of the entanglement entropy. But we also know that this volume law can be broken to an area law. The paradigm model is that of many-body localization, in which a sufficiently strong local disorder can localize the states, and localized states will have an area law scaling of their entanglement properties. So what we are looking here is the same physics, so this same transition from volume to area law, but for an out-of-equilibrium system. And the idea here is to use measurements to play the role of the disorder plays in many body systems. So use measurement to localize the state of the system. So why measurements? Well, that's pretty basic. This is a Zeno effect, the reason because of that. And this is because measurement compete with unitary evolution. So if you look at a qubit and you have think of a couple of states like spin up and spin down, and you have a unitary evolution that tries to create quantum coherent oscillations between the spin up and spin down states. If you intercalate this unitary evolution with measurements, and you have this simple drawing in terms of circuit here, and if the measurements, projective measurements are done frequently enough, then the state of the system is mostly localized in one of the eigenstates for most of the time, with very rare jumps between the eigenstates. So this basic physics can be exploited in the many-body scenario, and this has been done. Actually, it's very recent. Recently, it's been done only very recently. So what you see here is a circuit which is a generalization of the simple single qubit to a many-body context. So what you see is unitary evolution which couples nearest neighbors spins, and you can, in the simplest formulation, you can take this unitary evolution to be a completely random unitary matrix for 2 spins, so from U4, and then the next step, you couple with same unitary matrix the alternating spins. On the long time scale, this is equivalent to having some sort of random local Hamiltonian, and you expect a complete volume law scaling of the entanglement entropy after a long time. Now, if you intercalate this with measurements, if you measure everywhere projectively the spin up of the system, the state will always be non-entangled, will be always after measurement just a sequence of spin up and spin down, or weakly entangled nearest neighbors. So you expect an area law and no entanglement whatsoever. So the parameters by which you can control a transition here is the probability of measuring at a given site, at a given time. And by controlling this probability, you see transition between a volume to an area law. So what you see in the picture here is the time dependence of the entanglement entropy for the first case for very small probability, and second figure for very large probability. And you see that they saturate after a certain time to a value of the entanglement entropy, which in the first case scales with the system size, while in the second case for large probability is pretty stationary. The key results here is that this is a phase transition, a genuine phase transition. At the critical value of the probability, in the thermodynamic limit, you will obtain a phase transition, and you can, by finite size scaling, identify the universal exponent for this transition, which has been done recently. Now, the next step is that you can generalize this to many other models. So there are models in which you use Clifford algebra circuits, for which an exact mapping to percolation transition has been found. But you can also make other generalization, and in principle, you can consider continuous measurements. In this case, rather than projective measurement, your evolution is continuous in time and will be described by some stochastic Schrödinger equation. So this will become a random walk in the space, in Hilbert space of the system. So this would be for a single qubit if you measure the operator as Z. And in this case, there's no probability, but it's rather the coherence induced by the measurement, or let me also call it the measurement strength. So the process is a binary process with a nonlinear term here and Gaussian distributed noise. So we analyze this circuit as well. And what we find is also in this case, there's a phase transition. The results are obtained mostly by finite size scaling of numerical results. The only difference is the universal exponent of the transition is pretty different from the continuous case from the stroboscopic one. So there's a hint that this might be different transitions. Anyhow, the message is measurement, be it projective or be it continuous, induce a transition in the average steady state entanglement entropy of the system, which either scales as volume law or as an area law, as long as we take these results have been obtained for one-dimensional spin chains. Now, what I want to do is to look at a slightly different system now, which is free fermions in 1D. So we'll consider unitary dynamics originating from hopping of electron on site. So this electron can hop between different sites. And then the new unitary part consists in local measurements performed everywhere, independent measurements of the position of the particle, or if you want, of the density or of the charge, if you're thinking about electrons. So what this measurement do, which is the non-unitary component of the stochastic Schrödinger equation, will try to localize particle in states of the form 0, 1, 1, 0. So the kind of dynamics you expect from this model is exactly the same as described before. You have a competition between the measurements and the unitary dynamics. And indeed, that's what you observe if you simulate the system. So what you see here is the entanglement entropy for different system sizes as a function of time. So what you see is that if gamma, which now plays the role of the probability, is rather small, the system saturates to a value that scales with the size of the system, n in this case. So this would be some sort of volume law, take it with a pinch of grain. If you increase the strength of the measurements or the coherence rate, if you want, You look still at steady-state entanglement entropy, and you see that the average value of it does not scale any longer with system size, and we would refer to this as an area law. So the system for free fermions in this study is slightly different from interacting spins. Well, not slightly, a substantial difference. So the only parameter again is the phasing rate or measurement strength, if you want, and if you make it indeed strong enough, it's been found that you are in an area law. So the system is stuck in eigenstates of the operator you try to measure. If you decrease your measurement strength, you do not obtain a volume law, but you obtain a size-dependent scaling of the entanglement entropy, but this is logarithmic scaling. So this is sub-extensive, or if you want a critical scaling region. A volume law is possibly obtained, but it's just a finite size feature effect. In the true thermodynamic limit, only a sub-extensive critical region survives. Good. So what we want to do now, and where does the topology, which was in the title of the talk, come from? The topology comes from a second measurement. So what we want to do, we want to use this kind of transitional entanglement to explore some properties of many body systems. And in particular, we are trying to look at different phases which are different topological order. So one way to do that, and the way we are trying to follow here, is to introduce yet another kind of measurement. So the system now has both a unitary evolution with electron hopping from side to side, as a measurement that tries to pin electron on site, but also as a second measurement. Now, the operator you try to measure here, and how to do that is a different story. I mean, we can discuss it separately if you want. But the idea is that to measure another operator, which is the density now of a different fermion, and this fermion is constructed from nearest neighbor's sites. You see here the formal definition of this operator. So this is the crucial point. What is this operator? Because if you look at this second measurement we introduced, and you ask yourself, what are the fixed point of this non-unitary part of the evolution, which would be the eigenstates of the point of the operator you're trying to measure, those are the eigenstates of these D dagger X, dx operators, and these are the eigenstates of a topological Hamiltonian in 1D, which is a Kitaev chain. So this model will have a topological order with a twofold degenerate of the ground state, where the degeneracy corresponds to the presence of Majorana zero modes at the edge of the chain. So once you have this topological order, which will be dictated, so if you only have this form of evolution, every state will evolve to some eigenstate of this Hamiltonian and will display some sort of topological order. How can you identify that? We need to modify the entropy, won't do it, so we need to have some construction based on the entanglement entropy, and this is what's called the topological entanglement entropy. So this object, which was originally proposed by Kitaev, Preskill, Levin, and Ben, is essentially constructed by building different cuts of the system, as you see in the picture here, and constructing suitable addition and subtraction of the corresponding entanglement entropies. And these signs and addition and subtractions are carefully chosen, such that if you have some local states, these cancel. But if you have some localized states which appear at the edge of the system due to topology, so they have no local nature, they will survive the cancellation. So in short, this object is constructed such that if you have a trivial topological phase where you might have some disorder and some localized state due to disorder, this returns you at 0. If you have some localized states at the boundary of the cuts which emerge from a topological order, this will return you 1. So this is a quantity one can try to use and see whether the idea of what you're going to do now is to use this indicator of topological order and to explore how it behaves in the presence of the entire measurement dynamics and in presence of unitary dynamics as well. Now, similar studies have been done, but have been done only for projective measurements and symmetry protector and different topology due to symmetry protected with Z2 times Z2 topological order. And what they showed is that indeed this quantity seems to be successful and can be used to identify trivial, the topological, and the volume law area in the phase diagram. So what we are doing here is asking how does this quantity behave for continuous dynamics generated by a stochastic Schrödinger equation for free fermions in 1D. So the machine is mostly numerical. One solves this stochastic Schrödinger equation, looks at states, and calculates the entanglement entropy, repeats for all the realization of the stochastic process, and averages that. The only caveat is that this new measurement we are using here does not conserve the number of particles, so now we can generate or annihilate pairs of particles nearest sites. So the space to be explored is larger, but it's still only Gaussian states, which allows us to perform simulation to a larger number of sites, larger than up to 256 for sure. So let me come to the beginning of the results. So the first part of the results concerns what happened when you do this analysis for this fermionic model. So the first part of the analysis is the simplest one, in which you only have two measurements. And these are two competing measurements that try to establish two different orders, either a trivial one, which is a measurement of local densities, or the measurement of this that we call Kitaev operator, which tries to drive the system to eigenstates of the Kitaev Hamiltonian. Now, what you can do, you can study the topological entanglement entropy as a function of the two parameters, gamma and alpha, which are the prefactor, or if you want, the coherence rate induced by gamma is the coherence rate corresponding to the trivial density measurement, and alpha is the coherence rate corresponding to the topological one. So the color plot here is a plot of topological entanglement entropy, which scales from 0, as you expect, in one regime to 1 in the other. Of course, the only parameter in this model is the ratio alpha over gamma. And due to a self-duality which exists in this special limit in the lac, when the unit evolution is lacking, one can theoretically deduce that the transition between these two phases should happen. If it exists, it happens only at alpha equal gamma. Anyhow, this is a good toy model to see how studying the topological entanglement entropy can give us information about that. So apart from the color plot, which shows crossover to the fact that we're looking at finite size systems, how can we extract the transition, and whether topological entanglement entropy is a good indicator for that is the question we'd like to address here. And it turns out it is. If you look at the plot here, this is a plot of the topological entanglement entropy as a function of alpha for a fixed value of gamma. As we said, gamma equal 1 is enough, since the only parameter is alpha over gamma. And what you see is a well-defined crossing. Here we have data up to, I think, 128 here. So what you can show is that if you look at the crossing between the curve for a given size L and the following up size, 2 to the L plus 1, they cross at a given point, and you can repeat the procedure and extrapolate for large L, and this sits squarely at alpha equal gamma. But this, again, it's fixed by the self-duality in this specific case. What you can extract by this numerical analysis, you can extract a universal coefficient for the finite size scaling of this data. So you can try to finite size scaling the data in the vicinity of the crossing, which is done here, and aim at collapsing them onto each other with a single function. And this would give you a universal scaling, universal exponent for finite size scaling, which is nu equal 1.78. What you learn from that, you can compare these numbers with one which had been obtained still from numerical simulation in a system with stroboscopic dynamic and projective measurements. And again, there's a transition as well, but this universal coefficient scales in a different way. So the universal exponent seems different, which is, again, maybe a confirmation that the phase transition for continuous model might be different from the phase transition of projective stroboscopic models. Now, if you add also the unitary dynamics, of course, the phase space becomes much richer. We can plot it in this triangular plot. What you see here, the three extrema are the extreme case of the dynamics. So you have either gamma equal 1, which is a trivial case, in which you're only measuring local density. Here you're only measuring the type operator, and here the system is evolved truly unitary. You can plot both the topological entanglement entropy or the half-cut entanglement entropy, and you see, of course, variations to the corresponding corner, but it's hard to determine a transition just from this plot. You have to perform a finite size scaling similar to the one I described before. So the way we do it is we take the system, we fix one value of lambda, one value of gamma, and we change alpha. This would correspond to a straight line in this triangle, which starts from the corner alpha equal 1 and hit the fixed value of gamma on the other side. And you see the results in the panel C here. So if you plot as a function of alpha for different system size, and system size goes from small to larger, from blue to greens, you see that for small value of alpha, as you increase the system size, the topological entanglement entropy decreases. Then there's a region in which the topological entanglement entropy increases with system size. And this keeps going until a large value of alpha. Actually, what you see here is a slight dip. And this is what you would expect. In the thermodynamic limit, you would expect the system, all the curve to collapse to a single point here and then open up again. So you would expect a minimum to mark yet another transition. This is a feature of this free fermion system. You need to go to very large system size to observe some of this feature. Luckily, in our case, we can still take advantage of our duality between the two measurements operator, and we can construct a sort of a dual topological entanglement entropy, which is what is reported in panel D. And this dual topological entanglement entropy shows now a crossing at the other point where you would expect a minimum from the standard topological entanglement entropy. So the combination of these two data allows us to draw several points and mark lines from a transition. Now, the other point is to characterize what these transitions are. And there is a difference compared to all the other, projective models or the interacting one. You have an area law here, which is trivial, and your topological entanglement entropy would scale to 0 if you take the thermodynamic limit here. You have another area here in which your topological entanglement entropy scales to 1, or if you construct the dual one, it would again scale to 0. Which is you would expect here in this part. Now, the point is that there's still transition at any point, and this transition is now not to a volume law, which does not exist anyhow due to the having only free fermions in this model. And this remains a critical scaling region where the topological entanglement entropy has a volume law scaling. Now, these are the main results that we find by simulating the system. Now, there's one extra bit of information that we can add, and this is specific of the model that we have. So we're taking really advantage here of having a stochastic Schrödinger equation. And what we like to do is to see whether there's a way to associate this topology to any topological invariant. It's hard to do that, or at least I have no idea how to do that for the steady state of this system, which is obtained by a stochastic unitary evolution. So what we can do is to look at a simplified version of the model. And this can really do it due to this stochastic Schrödinger equation. What we can do is a post-selection, look at some post-selected corresponding dynamics. So what we do, this is the original model I looked at. Instead of following the entire stochastic process, we decide to pick up, pre-select, decide in advance, that's better, a certain well-defined readout. Let's say I only retain results if my detector returns the outcome 1, 1, 1, 1, 1, 1, 1. And I do this for both measurements. If I do that, since I fixed the readout of the detector, the back action into the system will be completely fixed. So I obtain a deterministic evolution from my system, which corresponds to a non-emission dynamics. Now, non-emission system have been mentioned, I think, yesterday in the talk. The point is that now that we have a non-emission Hamiltonian for this is a very specific trajectory of all the possible that one can consider, but we take one which corresponds to the the detector readout, which is maximum for the eigenstates of the measured operators. And the reason to believe that is that the system will probably form a cluster around this value, where the cluster will be given by the fluctuation of due to the measurements. Anyhow, if we focus on this specific deterministic evolution, we obtain a non-Hermitian dynamics, and for this non-Hermitian dynamics, we can perform an analysis of its topological properties, and that's what you see here in the black lines. So what you see is three phases here as well. There's a gapped phase, which is trivial, so a normal gap, and this corresponds to having a very large gamma. You have a phase with a very large alpha, in which the system is also gapped, but now you can construct a non-Hermitian topological invariant. I'm not entering now to do that too much, but you can construct explicitly a topological invariant for this phase. An intermediate phase remains a gapless phase. Now, what is relevant is that if you look at the black curves here, which marks the boundaries of the non-Hermitian Hamiltonian, they are quite different from the one you obtain from topological entanglement entropy of the full system. They would sit roughly along these white lines here. Anyway, what we find out is that these two processes are not so different from each other. What you can actually do, you can perform a sort of partial post-selection. So instead of retaining a single outcome from your detector, you can restrict the value that you obtain from your distribution of outcome of your detector. And you can ask what happened to topological entanglement entropy for this partial post-selection case. So here it's what happening when I restrict the distribution more and more towards one eigenvalue. You see that white lines are moving, and actually when you post-select large enough, they continuously move to match the post-selected dynamics. So the message of this part is the fact that this topological entanglement entropy that you can associate to the full measurements is continuously obtained from the topology that you can associate to the non-Hermitian Hamiltonian that you can obtain from post-selection in the system. I think that this is the last result I wanted to present, so I'm going to conclude. I hope that there are at least two basic messages that came across. The first one is that measurements can induce an entanglement transition in a steady state of an out of equilibrium many-body system, and this is a transition from area to volume law. If you have different measurements competing and non-commuting that compete with different order, you can also have the phase transition between different topological phases, at least for fermions in 1D. And the topological entanglement entropy is a good indicator of this phase transition. And finally, the last bit of information is that if you want to associate a topological invariant to these phases, this cannot be done directly, but there's a continuous deformation of the phase space to that of a non-Hermitian Hamiltonian, which has different topological order. You can use those as a way to classify the topological order for the fully measured one. Now, these kind of systems have only recently people have started studying those. So there's a lot of things that we don't know, a lot of things that eventually one can do. Some coming from the use of measurement, like using feedback and control. And the other advantage would be to use techniques that we know from free fermions and continuous dynamics to develop effective theories to describe this phase transition. With that one, I will conclude, and thank you all for the attention.
Okay, Alessandro, thank you for your very nice talk. We have just a couple of minutes for quick questions. Let's see if something happens on the web. No, I have a curiosity, which is mostly driven by the last part of the talk when you introduced non-Hermitian generalization of this stuff. Non-Hermitian models immediately reminds me to Limbladian dynamics. So, do you know if there is an extension to noisy systems of your formalism? For instance,
what do you mean by noisy?
Limbladian and non-Hamiltonian.
Yes, in some way there is. So, I mean, the system I'm describing have also a corresponding Lindblad equation. Maybe this is the kind of answer. You can certainly look at the same features for Lindbladian dynamics, but what I want to stress is that that's also what is being done here. So the post-selected model that I'm doing is in fact the result, the non-emission model that I'm looking at, which is a post-selected one, is described by the Lindblad equation if you want. The other point I want to make is that if you take the original model in which you have the stochastic Schrödinger equations, if you average over the stochasticity of the process, you obtain an effective Lindblad equation. That Lindblad equation, anyhow, has no information whatsoever about the entanglement of the system. The steady state of that Lindblad is the completely trivial state for the system, completely mixed one, so there's no entanglement information you can extract from that. And I think that this is a key point of using measurements at the technical level, at least to look at these dynamics. The point is that if you have an unraveling of those Lindblad equation in terms of measurement of local measurements, for each of the quantum trajectory of that unraveling operation, you will always be evolving a pure state. For that specific pure state, you can calculate the entanglement entropy of by partial tracing. And this gives you some information of the entanglement on that specific trajectory, and then you average. So most of the physics you see here is about averaging over the stochasticity of the measurement and nonlinear function of the density matrix of the system, which is the entanglement entropy. If you had to average a linear function, you would not see any of the entanglement features that I described here. It would be completely oblivious to the phase transition I'm talking about. I hope this answer to your question.
Okay. Yes. Okay. So let me check. Okay, there are no other questions. So I thank all the speakers of this session, and we stop here for the lunch break, and we recombine at 2:10. Okay.
Thanks. Bye.
Bye.